Hello and welcome back. Now, unfortunately, I've only been able to make this video today, which is just one day before the exam. I was away previously, and well, then I was waiting for some new USB adapter to arrive. Right. So if you do manage to see this before the exam, well, hopefully it'll be useful. And I guess if not, well, for future candidates, right, hopefully this will also be useful too. Okay. So in particular, well, this is a walkthrough of the February-March 2026 paper, and that's going to be variant 12. All right. And yeah, there is only one variant in the FM series. Okay, so question 1 says, tick one box to show which statement about data storage is correct. Okay, so well, A, right, 1 bit equals 4 nibbles. Now, I think that's actually going to be the opposite, because if we think, well, 1 nibble is going to be 4 bits, right, so that's kind of what the opposite way around. They've mixed them up. Okay, so B, well, 1 byte equals 16 bits, right, so that's going to be wrong, because, well, 1 byte is going to be 8 bits, right. Now, I guess if you want to go the reverse, where you say, what's 16 bits? Well, that would then be 2 bytes, so of course that's also wrong. C, right, so 1 exabyte is equal, well, to 1024 times 1024 tebibytes. Right, now actually this one I'm not entirely sure about. I guess I've kind of forgot that. Right, so what we can do, well, let's go to D, and then maybe process of elimination, we can see which one's actually correct. Right, so D, 1 mebibyte equals, 1024 times 1024 gigabytes. Now, again, I think that's actually also kind of the wrong way around almost, right? Because if we think what mebi is going to be smaller than gibby, right? So in particular, I guess what we would say, well, 1024 mebibytes, that's going to equal, well, to 1 gigabyte, right? So this is also the wrong way around, right? Therefore, I guess process of elimination, that must be C that's correct. Right, then B, so an image file has a resolution of 1024 pixels high and also the same 1024 pixels wide. The color depth is 2 bytes. We want to calculate the file size of the image and also give the answer in mebibytes, right, and also show you're working. Now, actually, this question is quite easy because if we think the formula, formula for image size, that's going to be resolution, right? So what the number of pixels wide and the number of pixels high, then multiplied by the color depth. Right, now because here, this is in mebi, and then also it's going to be in bytes. So if we think, mebi, right, mebi is just 1024 times 1024. So if we have, 1024 times 1024 pixels, that's basically going to be kind of like mebi pixels. All right, so let's just kind of write that. Let's say 1024 times 1024. That should be a 0 there. All right, that's going to equal, I don't know, let's say, right, 1, I guess we say like mebi pixels. Right, so that's going to be the number of pixels. Now, what we then want to think, kind of how much memory or how much data is 1 pixel. Now here they've said, just 2 bytes. And actually, because here the answer is also in bytes, then we can just multiply this by 2. Right, so let's go, sort of 1, let's say like mebi pixels, I guess. Right, multiplied by, that's going to be 2 bytes. Then that's just going to equal, 2. Alright, so that's just going to be our final answer. Now, a lot of these questions often they have, maybe like 512, say multiplied by 2048. Now, if you think about that, if you think about sort of make everything in terms of 1024, then we think the 512, that's just going to be 1024 times 0.5, or of course half of that. 2048, that's obviously 1024 times 2. Right, so I think if you do that, then you can sort of cancel out the multiply them all together, cancel out the fractions, etc. Alright, so I think often some people say, how do I multiply these huge numbers together? Right, but again, they're always going to give you kind of answers that you can simplify, and again, cancel out the fractions. Okay, so a user accesses a website using a web browser. 2 functions of a web browser are to provide an address bar and also to store cookies. We want to give 3 other functions of a web browser. Okay, so let me just type this because I think my handwriting is not good. Alright, okay, let's move it down. Right, okay. So I guess 1. Now, probably what we can say initially, I guess you say what it's going to basically submit web requests. So, that can be HTTP, HTTP, right, and also HTTPS. Now, I guess there are also some other protocols. So let's maybe say that, let's say, right, to implement, I don't know, let's say protocols, right, such as, let's go, HTTP, let's put S in brackets. I don't know, and to, let's say, send, send request. Okay, right, let's say that. Let's say and send, right, slash receive requests, right, request to and from a server. Yeah, okay, right, okay, well, let's be more specific, right, let's say web server. Alright, so that, okay, that should be one. Now, I guess a second thing we can also say, we can probably say what it's going to basically render the, render the HTML, right, render the CSS. So let's say that to render, alright, and okay, so I guess we could also say, maybe to parse. Let's say, alright, to parse, alright, and also when we say parse, that basically means, well, take a string of code, right? So it could be HTML, could be CSS, could be JavaScript, right? And then, well, just sort of execute, kind of execute that code. Yeah, I guess, or, say apply the sort of styling rules if it's CSS. Right here, let's say, yeah, to parse, and execute, right, / apply rules, for various languages. Right here, well, let's say, yeah, IE. Right, that's going to be HTML, CSS, right, JavaScript. Well, okay, yeah, let's go JavaScript. Right, we'll write out the full name. Alright, and I guess say what, and hence render the web page. Right, and hence render the web page. Yeah, I don't know, like as kind of UI elements for the user to interact with. Alright, so hopefully that makes sense. It's just what sort of converting the code into, again, buttons, images, just things the user can click on. Alright, then I guess number 3, well, let's go with something a bit more simple. So we can probably say what to kind of store history. Alright, so I think for these, often they'll say, well, to store web page history, I guess also to, provide a back button, right, forward button, I guess also sort of favorites. Right, so let's kind of say that. Now, I think I'm going to say, well, the history and also back and forward, because again, they're kind of related. So let's say to store the user's, I don't know, sort of browsing history, sort of page history. Okay, let's kind of say both of that, right? So page, right, / browsing history, right, and I guess provide, I don't know, yeah, back and forward buttons, I don't know, yeah, for them to navigate. I don't know, yeah, like to the pages they've sort of previously visited. For them to navigate, yeah, to the pages, right, that they previously visited. Alright, so I think that's kind of all the main ones. Alright, now I guess also, okay, so I think that's kind of all they say. Alright, I mean, you could mention something about kind of encryption, but I guess we've also kind of mentioned that here, as well with the HTTPS. Right, then B, so the user enters a uniform resource locator or URL into the address bar of a web browser. The URL is converted into an Internet Protocol IP address, and we want to describe the purpose of an IP address. Alright, and that's only one mark, so I guess we just need a simple definition. Okay, so I think the definition for an IP address, well, if we just say to uniquely identify a device on a network, and then I guess we can say, well, so that packets, right, or data, can be sent, obviously, well, between that device and other devices. So let's say something like that, right, to uniquely identify a device, right, on a network. I guess so other devices can communicate with it. Okay, so let's maybe say to allow. Alright, so to allow other devices, right, to, communicate. Let's say communicate with it. Alright, and I guess that also sort of indicates, communicate being kind of two-way communication. Alright, but I guess we could be more explicit on that. So let's say, to allow other devices to communicate with it, I don't know, let's say like back and forth. Alright, and I guess we could also say by sending packets. That's just sort of a bit more technical, using the correct words. Right, okay, then, part 2, we want to explain how a URL is converted into an IP address. Alright, so basically, that's asking about DNS, domain name service. So I think, domain name system. Alright, so let's actually just go and have a look at this, because I do actually have some diagrams here. Alright, now the first one, this is quite complex. Alright, so in fact, do we have the pen? Okay. So here then, obviously we're trying to go to this, mypage.com. Right, now actually first what we can see, first actually we're going to check, does the computer sort of already know this IP address? Alright, so does the computer know the IP address that maps to this mypage.com? Right, and there's really going to be a few places that it can check. Alright, so first it's going to check, in the local cache. So basically, well, that means the web browser. Right, so when you go to a website, I think, well, temporarily, the web browser, for example, Google Chrome, that will kind of temporarily store, right, those recently visited DNS records. All right, so if the web browser doesn't know, well, then it can ask the operating system. I guess that will also store. All right, and I think in particular as well, we can also manually set some DNS records, for example, in the host file. All right, now you actually don't need to know this for IG, but yeah, it's kind of interesting maybe for some people. All right, now if you're on Linux, well, that's going to be in what etc. I think what is it hosts? No, I think there's an S on that. All right, now if you're on Windows, it's basically going to be the same. I think you have to get like Windows System 32. Yeah, maybe, I don't know, like sort of drivers, etc host or something. Yeah, I sort of can't remember the exact file path. Right, but if you do want to see that, and then just to kind of modify the DNS records, or to kind of add your own DNS records, then again you can just search how to modify sort of DNS records on Windows, and yeah, obviously sort of search for the host file. Alright, so that's kind of the first stage, where it's basically going to check your computer. Alright, so if your computer, and again, well, that's the browser and that's also the operating system, if they don't know, well, then it's going to go to the router. Alright, obviously check the router. Now, if the router doesn't know, alright, and I think here I'm sort of going to go to this diagram, because honestly, I mean, this diagram here, well, this first diagram is then a bit confusing. Right, so if the router doesn't know, well, then it's going to go to the ISP's DNS server. Right, if the ISP's DNS server doesn't know, well, then it's obviously going to go to these kind of global DNS servers. All right, okay. So I think, again, I mean, you don't really need to know this for IG. If you just say, well, it will sort of check the global DNS servers, that sort of should be enough. All right, but specifically, well, first it's going to ask, I guess, this root DNS server. All right, so what that will do, let's say if you have like a .com, right, domain, well, then it will basically say, okay, if you have a .com domain, well, then you want to go, let's say, to this specific, say .com, well, top level domain server. Right, now let's say you have I don't know, let's say like a .org, right? If you have a .org domain, well then, okay, where's the mouse? Okay, here we go. All right, so if you have a .org domain, well then, for example, you might have, some other top level domain server, right? That just knows, well, sort of where to send the sort of, .org, requests. All right, so then actually what's going to happen, actually these top level domain servers, they're not going to store all of the, DNS records for .com, right? Because actually it's kind of not as simple as, well, just, one website has one sort of DNS record, right? Because actually, well, each subdomain, so let's say you have, I don't know, maybe let's say a.google.com, for example, right? So that's actually going to be a different DNS record, let's say for the, a dot, right, compared with just the regular google.com. Right, so actually these top level domain servers, they're not going to store all of them, because again, there could be hundreds of DNS records just for one particular site. There's also going to be sort of like mail records, like email records, various other things. All right, so what they're going to do, they're basically going to sort of know who to ask. Now, let's say if you're hosting on, I don't know, say like hosting or like GoDaddy or any of those popular kind of web hosts. Now, actually, what's going to happen? Like most likely, well, this this kind of .com, top level domain server, right? Basically, you would have said, well, I'm hosting my website on, again, GoDaddy or what sort of whatever web host you're using, right? Then it will say, well, if you're going to, this particular website, well, then, go and ask, say, like GoDaddy's, DNS server, right? So that's kind of what they're saying here with the authoritative name server. It's just kind of asking the specific, well, let's say web host, or the specific kind of DNS server provider that knows all of the DNS records, well, for this particular website. All right, so hopefully that makes sense. Again, it's kind of, sort of possibly complex, but I think, again, if you just think, I mean, it just, sort of starts starts on the computer. Again, checks the browser, checks the operating system. If that doesn't know, well, then it goes to the router, right? If the router doesn't know, well, then it goes to the ISP, or the ISP's DNS server, right? And if the ISP's DNS server doesn't know, well, again, then it's sort of going to check these sort of global, these global DNS servers, right, in this kind of three-step process. So let's sort of try and write that, and I guess we'll sort of try and write it more simply. Let's say first then, well, I guess if we just mention about the operating system and browser. So let's say first, the browser, right, checks to see, right, if the DNS record, Yeah, okay, right, okay, so, okay, let's sort of say what the DNS record is. Let's say, right, the DNS record mapping the IP, okay, no, okay, right, okay, sorry, what, mapping the URL, right, to the IP address. Yeah, let's make sure we get it the right way around. So, right, mapping the URL to the IP address. Yeah, I guess what is in its cache. Yeah, okay, right, is in its cache. Okay, let's see what, since the user, right, might have recently visited it. Right, recently visited that site. Okay, yeah, okay, right, okay, so, okay, let's say what happens if it is, right, so let's say if it is, right, if it is, I don't know, yeah, the, what, DNS, well, the DNS kind of propagation, yeah, or I don't know, the DNS request sort of is, well, I guess sort of handled, right, the DNS request, let's say maybe is fulfilled, right, fulfilled, yeah, and the process stops. Alright, okay, so, okay, let's say here then, well, what if it's not? So if not, right, the process continues. Let's see what, checking, yeah, checking the operating system. Right, let's say what then router. I don't know what then. Okay, right. Okay, let's do. Okay, right. Okay, let's go. What then? What ISPs? Right. So ISPs, DNS server. Right. Let's say yeah, and finally, what a series of global. Alright, and like okay, yeah, okay. So okay, let's say here then we can be more specific, right? Give the names. So global, if we remember, well, first it's going to be the root, then it's going to be what, the top level domain server. Right, top level domain server. Right, and well, let's see, yeah, and finally the authoritative name server. Right, the authoritative. Yeah, okay, right. So authoritative name server. Alright, and I think possibly that's spelled with an I, even though I thought it was spelled with an A. Yeah, I think I saw someone spell it with an I. Yeah, right, okay, so I guess it's probably like this, authoritative. Yeah, it's probably spelled something like that. Yeah, okay, right, okay, so right, and finally a series of global DNS servers. Well, let's say, yeah, until a match is found. Alright, so I think that should be fine, and then I guess possibly we could say it could then be cached at the previous stages. So let's say, right, okay, when the DNS, yeah, the DNS record is found, let's say what, and returned, or I don't know, well, let's say, right, sent, okay, right, sent, I don't know, yeah, back down the network. Right, let's say then it's cached, right, cached at each stage. Well, let's say, yeah, temporarily. So that, I guess, what, new users who try to go to the same website, what, the DNS service. Okay, no, sorry, the DNS request doesn't have to be performed kind of in full again. So let's see that, right, okay, so that, let's say users, right, who, okay, let's say, right, visit, or yeah, I don't know, you know, try to visit, right, try to visit the same site, I don't know, let's say, what, in the near future. Right, in the near future, what don't trigger, what I guess the full kind of what DNS kind of queries, yeah, query stages. Or okay, let's say I maybe trigger all DNS query stages. Yeah, just so the grammar kind of makes sense. Right, okay, then C, so the website stores cookies on the user's computer, and we want to state what is meant by a cookie. Right, so I think this one is hopefully not too difficult. We just need to remember the definition. Right, now I think usually, well, they say it's a text file. Right, so we can say, well, basically what a text file storing data. Right, a text file storing data. What, let's say about, well, the user's kind of browsing activity. Yeah, I don't know, well, let's say browsing activity, or slash, I don't know, maybe settings, I don't know, sort of like preferences, right, I guess, etc. Yeah, I mean, that's probably enough. All right, and I guess we could say, well, it's sort of stored by the web browser. Yeah, so let's maybe go back, right, so text file storing data, I don't know, well, okay, let's say from the web browser. Yeah, okay, right, let's say from the web browser. Right, okay, yeah, what about, let's say, well, about the users. Alright, so what about the user's browsing activity, settings, preferences, yeah, etc. Alright, so I think that's fine. Right, okay, then part 2, we want to give one example of how a website can use a session cookie. And also one example of how a website can use a persistent cookie. Right, so the difference then, well, when it says session, basically, while that's like a temporary cookie, right, that's only going to last while the user has the browser window open. Okay, so as soon as they close their browser, yeah, I guess also well, as soon as they obviously turn off their computer, well, when they then open it, let's say the next day, well, then it's not going to be there, right? So if they close their browser, well, then that cookie is deleted. Right, now this is also, let's say if you're using a private window, right, if you're using, well, say like incognito in Chrome, now actually that's also not going to persist. Yeah, I guess, well, that's also the same for persistent cookies. Yeah, they also don't persist, right, if you're using a private window. All right, so let's kind of say that, let's say what a, okay, so here then I guess they actually want an example. So I think for a session cookie, well, if we think some kind of temporary data, that could be what the user's shopping cart. So let's maybe say that right to, I don't know, temporarily store the user's shopping cart, shopping cart on a website, what, let's say until they close the browser. All right, so I think that's fine. All right, then persistent cookie. Well, this is going to be something more permanent. All right, so let's say, for example, we have a website. Well, if there's maybe some user setting that we want to be permanent, right? So for example, let's say their language choice, because let's say, well, if they choose, I don't know, to sort of show the website in Spanish, well, most likely they'll always want to sort of, you know, load the website in Spanish. Yeah, I guess kind of every time they use it, right? I guess other things, let's say, you know, light mode, dark mode, right? That could be something we could store. So I think any kind of preference like that. Now, if you think, let's say, well, like the pseudocode, right? Well, sort of, you know, pseudocode pro. Now, something that's stored, well, I guess that's actually what sort of local storage, but I guess you can also sort of consider them what sort of cookies as well. That's actually going to be like all of your programs. So when you click, you know, create new program, well, that's basically like going to be a persistent cookie. Yeah, I guess technically it's well sort of local storage, but again, it's kind of the same thing really. All right, so when you close the browser, well, again, if you're using a non-private window, well, next time when you open it, right, your previous programs will sort of still appear. Yeah, well, they're going to be saved, right? They're going to be persistent. Now, again, if you're using what like a private window, actually, well, no cookies are going to be saved regardless. All right, so let's sort of, I don't know, give like a language preference, for example. Let's say, I don't know, what some user settings or preferences. All right, let's say, yeah, for example, their language choice. Right, their language choice. I don't know, yeah, for the UI, right, of the website. All right, so hopefully that makes sense. Then question 3 says a drone is used to search for lost animals. The drone's a flying device that can be autonomous, okay, so it can be well operated by itself, what sort of kind of like without humans, right, or it can be operated using a remote control. So the drone's a robot, and we want to give 2 characteristics of the drone that identify as a robot. Right, okay, so this, when they ask, well, basically, what is the definition of a robot? Again, there's always 2 parts, right? So one, they say, well, it's going to contain kind of electronic components, right? Also, it's going to have, well, mechanical components. So yeah, let's kind of say that, and then maybe we can also give more details. So let's say, right, it contains, I guess, well, electronic components, right, components. Well, let's maybe give an example, right, e.g., I don't know, yeah, a CPU, or, well, I don't know, yeah, some like microprocessor. Right, microprocessor, I don't know, what, let's say memory, right, storage, yeah, I don't know, what, let's say like sort of like wiring, sort of, yeah, I don't know, some like wires, right, motors, right, let's say etc. Right, I guess also cameras, let's say, right, cameras, sensors, right, etc. All right, and let's say what that can be pre-programmed. Yeah, I guess, well, let's say, right, that can be programmed to perform, let's say, what specific tasks. Okay, so I think that should be fine, right? Then part 2 again, we said, well, it's going to contain mechanical components. All right, let's say it also contains mechanical components. Right, mechanical components. What, I guess that allow the robot to move. Yeah, I mean that's kind of, I guess, all we really say. Like, I can't really think of anything else we can say for that. Possibly you say, well, it contains mechanical components that allow the robot to move. Let's say what, yeah, and are controlled. Let's say controlled by the electronics. Yeah, I guess what, or the microprocessor. Right, controlled by the microprocessor. Yeah, like kind of on board. Right, then B, the drone has a built-in system to stop it from crashing into objects, for example, a tree. The system uses sensors and a microprocessor, and we want to identify one sensor that could be built into the drone to detect if it's near an object. Alright, so I think for this, I mean, if you just sort of remember the word, right, proximity, well, of course, proximity means, well, how close you are to something, right? So I think probably the most suitable one here, well, that's going to be a proximity sensor. Alright, so again, that's going to be used, well, just to detect kind of how close it is to other things. Right, and I think usually the way it does that, I mean, it's kind of like radar, right? The sort of same way it works. Now, probably most of them, I think, are going to be infrared. Right, I mean, possibly they might be ultrasound as well, but I mean, yeah, I think probably mostly infrared, right? So it's going to be active, right? So when we say an active sensor, well, that's a sensor that basically sends out a signal. Then, for example, it can like wait for it to hit an object, right, rebound, and then of course it can measure how long it takes for it to rebound in order to determine how close it is to other objects. Right, now, when we say a passive sensor, because I think they do ask this sometimes, when we say a passive sensor, well, that's going to be a sensor that's just sort of like listening while sort of receiving signals. It's not actually sending out any signals. All right, so to kind of give an example of that, I think a common case where an active sensor is used, that's going to be in smoke detectors. So let's just sort of try and draw this quickly. Yeah, I'll just kind of go up here. All right, so what you're going to have, let's say you have, well, the bottom of the smoke detector here. Right, now let's say we have some kind of, I don't know, some kind of infrared emitter. Right, then let's say at the top, well, then you're going to have some kind of infrared, well, let's say some like infrared receiver. Right, so here it's obviously going to be sending this infrared signal between these. Now, let's say hypothetically, right, if there's like no dust, right, no smoke, well, then it's obviously going to be receiving this at kind of like 100% signal strength. Now, let's say if there's a fire, well, if there's a fire, right, of course there's going to be, there's going to be, smoke and, yeah, obviously dust, right, particles, whatever. All right, so if okay, let's just sort of do that there. All right, so if we have that, well, then I guess some of the infrared is actually going to be blocked. So then, for example, rather than receiving 100% of the signal, obviously by this kind of receiver here, well, instead, let's say we only receive 50%, right? So if we have that, so what if the reading goes below a certain sort of threshold, I don't know, maybe let's say like 90% of typical level, well, then what the microprocessor, that will then cause the alarm to start. All right, so hopefully it makes sense. And again, that's going to be an example of an active sensor because again, we're actually sending out a signal. Well, in this case, we're sending out, for example, infrared, right? Whereas if we're talking a passive sensor, again, that's only going to be receiving. All right, so an example of a passive sensor, well, let's say a temperature sensor, right, where that's basically just kind of measuring the outside environment. It's not sending out any signals itself. Right, okay, then two, right, so we want to state what is meant by a microprocessor. Okay, so I guess, well, basically it's just a mini CPU. So let's say, yeah, kind of how to word that well. Let's say it's a small, right, okay, let's say, yeah, it's a small, a small processor. I guess we can say we're embedded, right, let's say embedded into the device. What that can, well, again, fetch, decode, execute instructions. Right, okay, yeah, okay, right, okay, so, okay, let's say maybe it can control the device. Right, so it's a small processor embedded into the device. What that can control it, I don't know, yeah, by fetch, decoding, and executing instructions. Fetch, decoding, well, yeah, let's go executing. I don't know, yeah, sort of instructions. Yeah, I think that's kind of all we can say. I mean, possibly you could say what we're sort of loading them from RAM. So let's say that. I don't know, yeah, well, from like RAM or from memory. Yeah, I think that should be fine. Right here, then three, we want to explain how the sensor and microprocessor work together to stop the drone crashing into an object. Okay, 4 marks, right? So these questions they often have, and basically it's the same formula every time or the same kind of structure. All right, so I guess one, well, you're going to say there's, well, obviously sensors, right? Those sensors will be basically, well, continually measuring the environment. Those sensor readings, well, first they'll be converted. So I guess we would say it would use an ADC, right? An analog to digital converter. To convert it, well, obviously, yeah, from the analog sensor reading, to, let's say, the digital signal that the microprocessor can understand, right? That signal is then, of course, sent to the microprocessor. That will then basically compare it, well, I mean, kind of just like using some if statements, if you just want a simple example. So that can sort of compare it to some, say, like normal values. Okay, so let's say in this case, let's say a normal value is that the drone should not be within like 1 meter of something. Now, if, for example, the reading is that it's, sort of 0.9 meters from something, right, in some given direction, well, then what's going to happen? I guess you say what the microprocessor, that will then send a signal to the drone, right? For example, well, to obviously change its, or like change its direction or change its speed, yeah, I guess just stop moving. All right, so you can say, well, it's going to obviously send, well, it's obviously going to calculate the sort of new direction. It's obviously then going to calculate, you know, which, let's say, which like blades have to turn, yeah, like what angle they need to be, you know, various other things. Right, and then of course it's going to send a signal to the, you know, those particular components. All right, and then I guess you'd say, well, then there can also be what DAC, right? So digital to analog converter. That's again going to convert the digital signal into, let's say, some analog data, or yeah, some more analog kind of electronic signal that, of course, can then be used to, well, sort of, you know, change the motors, and well, yeah, change the angle, change the speed. Yeah, I mean that's kind of what they normally say, all right. And then I guess you say, well, this process is continuous. So it's obviously going to happen, you know, I don't know, sort of like hundreds or thousands of times, yeah, kind of every second in this case. So yeah, okay, so let's kind of sort of try and put that into words. Yeah, I was looking for the mouse there. Right, okay, let's say what these sensors, or well, yeah, it says what sensor, right? Yeah, okay, sensor, right, just one. Right, let's say the sensor, I don't know, what continually, yeah, continually records what data about the position or well proximity, right, to objects, right, and sends. Okay, yeah, okay, right. Let's say what sends this, or yeah, well, let's say I don't know, well, this is converted. So let's say that first. Right, let's say yeah, this data is converted. Right, this data is converted. Right, from analog. Right, analog to digital. Yeah, by an ADC. Well, let's say, I don't know, and forwarded onto or passed onto, forwarded onto the microprocessor. Okay, right, let's see what this, yeah, I know what this, I guess, compares. Right, compares the received data, what to an expected, right, expected normal sort of, yeah, value, or, okay, yeah, okay, let's sort of change that. Let's say, yeah, to expected normal, I guess, conditions. Yeah, I don't know what conditions or parameters. Right, okay, yeah, okay. So let's all be specific, right? Let's say, e.g., what, let's say what the drone shouldn't be within 1 meter. Yeah, okay, right, okay. Let's say that. Let's say the what closest, or yeah, the smallest. Yeah, right. Okay, let's say closest. All right, the closest safe proximity. I know, yeah, should be right 1 meter, right, from any object. Alright, so I guess, well, if it's sort of outside of that range, well, then we don't have to do anything, so it's safe. So let's say that. Right, okay, let's say if the received value rate is, well, greater than, right, or equal to the, I don't know, yeah, to the safe, right, slash normal value, right, then, I don't know, what, no action is taken. Okay, let's say else, yeah, else the microprocessor, what, let's say, will calculate, yeah, calculate, I know what the speed, right, speed and direction change, right, that is required, what, to, I guess, move the drone to safety, yeah, to move the drone, right, to safety, yeah, and, I don't know, prevent collisions. Alright, then I guess we can say, well, this data, so yeah, I guess, well, this digital data, right, is converted, what, into analog, yeah, okay, converted into analog, right, via a, well, DAC, so again, well, digital to analog converter, right, and let's say what, and sent to, yeah, and sent to the, well, I don't know, yeah, sent to the motors, yeah, I'm not, that's kind of what it's going to be using, right? I guess, like motors, well, I guess you say maybe rodders or something, right, let's say, yeah, motors, rodders, to what effect, yeah, I guess, well, okay, let's say correct, right, correct the drone's, well, I guess, like velocity, yeah, I don't know, so it, yeah, so it avoids collisions. Alright, so I think that's fine, and again, okay, okay, so here then, since we've got, you know, still one line left, I guess we can probably say, well, this process is continuous, even though we have sort of mentioned that here when we said, well, the sensor continually records, but I guess, well, let's just reinforce that. Right, this process, I know, yeah, is continuous, right, to prevent the drone, well, from colliding. Then if we look at CSS, the drone has a digital camera that records a video while the drone is flying. The drone can be connected to a computer using a universal serial bus USB interface. to transfer the video recorded by the digital camera. Right, then we want to state what is meant by a USB interface. Right, now I think some people were confused by this question, okay, but actually I think really this is asking, well, what do the three words, USB mean? Well, yeah, the three letters. Alright, so it's kind of just asking for the definition of USB. Alright, and also when it says interface, well, that's kind of, well, I guess you can say it's like a, kind of like a medium, or like a, I don't know, well, obviously some way for data to be, let's say, transferred from, well, one device or one format, right, to another format. Right, so when they say an operating system, well, that's sort of an interface, well, between the hardware, right, and the user. So it's kind of a way for, well, the user to interact with the hardware. Yeah, and I guess also vice versa, right? Because what the hardware, well, that's obviously like the screen. Yeah, that's outputting information to the user. Yeah, it's obviously going to be input output. All right, so it's kind of the same thing. So let's sort of mention that. Right, let's go. Maybe it provides. Right, and right, I guess I don't know, sort of input output or two-way communication. Right, okay, let's say two-way. Okay, well, yeah, okay, all right, okay. Let's say serial. Right, okay. Yeah, I guess that should be A, right? So a two-way communication. Right, two-way serial communication method. Or I guess, well, protocol. Right, communication protocol. Yeah, okay, right, okay, so here then, probably we want to say, well, what is serial? So we can probably just put in brackets, let's say what 1 bit, yeah, is sent at a time. Right, okay, so it provides a two-way serial, well, 1 bit is sent at a time communication protocol. Right, well, that is universal. Right, so let's say what that is, right, i.e., well, supported by many different devices. Right, many different devices. Alright, and then I guess we can say what, along a bus, right? So a bus, well, that just means a wire. Right, yeah, so let's say along a bus. Alright, so I think probably that's fine. So yeah, it provides a two-way serial, right? Well, serial communication protocol that is universal. Yeah, okay, right. Yeah, okay, right. That's okay. Alright, so I think that's probably fine. Now we could maybe just link it back to this particular scenario. So let's say, right, e.g., what it's going to be, what I guess, real time. No, okay. So it's not going to be real time. I guess it's after. Right. Okay. Let's say, well, that's going to be video transfer. I don't know. Yeah, from the camera, or well, yeah, from the drone. Yeah. Okay. Right. Okay. Let's say right from the drone, right to the computer. Right. Okay. Then to right. Right. Okay. Yeah. Okay. Right. So explain how a USB interface is used to transmit data. Right, now I think actually that's kind of what we just answered, so we can say again it's serial. Right, now I think also USB, I mean that should also be full duplex, yeah, probably. Alright, because I mean you're going to want to be sending data back and forward. Alright, so hopefully that's going to be the 2 marks. Now you could also say there's multiple wires. Now I think even though there's technically only 1 wire to send data, yeah, I could be wrong on that, possibly like USB 3 they might have changed that. Alright, but there's probably also other wires for, well, things like sort of clock signals, right, synchronization. Yeah, maybe there's some dedicated wire just for sort of interrupts and things like that. Alright, so let's try and mention some of that. So let's say, right here, yeah, it uses, and again, this is just repeating ourselves, it uses serial communication. Alright, okay, let's explain that. Right, let's say, yeah, where 1 bit, right, is sent, well, okay, yeah, okay, let's say, well, 1 bit is sent along the wire, kind of after each other, right? So I think we don't really want to say, well, 1 bit at a time, because it's not like there's only 1 bit on the wire at a time. There's obviously millions of bits on the wire at the same time, but I guess they're sent kind of in sequence. So let's use serial communication. Okay, right, let's say where the bits, right, the bits are sent, I guess, well, in sequence. I don't know, yeah, one after each other. Yeah, well, let's go right one after each other or one after another. Right, and I guess we can say what along a yeah, no, along a wire. Yeah, alright, well, let's say right wire or bus. Right, okay. So I think that's fine. Right, then again, we can probably mention the full duplex. So let's say full duplex communication, right, is also used. Let's say to allow two-way communication. Okay, well, two-way communication simultaneously. Right, right? And yeah, I'm not going to worry about the spelling, right? Let's say, for example, right, okay, so the drone, right, the drone sending video to the computer. Right, okay, sending, sending videos to the computer. Right, and then and the computer, I don't know, maybe sending interrupts or, for example, software updates. Right, and the computer, let's say, simultaneously, right, sending, what do we say? We said, I don't know, say like interrupts, or let's say interrupts, let's put in bracket, maybe status messages. Right, okay, yeah, I don't know, or like say software updates, right, to the drone, I guess at the same time. I guess we've sort of said simultaneously. Okay, so I think that's probably fine. Now, we could also mention, because again, it is 2 marks, but they did give us a lot of space. Now, I mean, hopefully, again, we've, matched 2 of the points, right? But you could possibly mention, well, there's also different standards. So let's go, let's say, right, USB, I don't know, also, I don't know what sort of has or supports, supports different protocol standards. I guess, USB, let's say consists of, consists of, let's go different, different protocol standards, or let's say protocol versions. I don't know, which support, let's say, different features. I guess bandwidth, or data transfer rate. I think that's fine. Obviously, USB 1, USB 2, USB 3. Okay, so then we want to draw an annotated diagram, or diagrams, to show, one, the contents and structure of a data packet, so networking, and also how a data packet is transmitted across a network. Okay, so let's try and do the first one, and it's probably really going to be 2 different diagrams. So here is the pen. So here then, probably what we want for the data packet. I guess we're going to have the data in the middle, and then of course we're going to have a header, right? And I guess we can also have a trailer as well. So let's just sort of label this, right, data packet. Alright, so let's sort of do that. Is obviously not the best drawing. Alright, so here I guess we can call it payload or data. Alright, so let's say payload. Let's go, for example, data. Alright, then I guess there's going to be a trailer. Right, now in the trailer, let's just sort of label that here. Alright, so in the trailer, I think mostly it's just, for example, some like CRC, or some like cyclic redundancy check. I think this is actually added in the Ethernet layer. So we can say, I don't know, some CRC or some kind of error checking code. I think there's also like a delimiter just to signify the end of the packet. So let's just sort of do that here. Let's say, I don't know. Okay, let's go like CRC. Let's say error check. Yes, it's kind of a bit difficult to sort of write small on this. And then let's say, I don't know, like frame delimiter. Alright, so that's going to be used to signify the end of the packet. I think that's kind of the sort of main things. Right, now if we look in the header, here there's going to be a lot more. Right, now we obviously don't need all of it, but I'm just going to sort of try and list, let's say at least 3 or 4. Right, so in the packet header, one, there's going to be the source IP. Right, so that's going to be our IP. Now the reason we need our IP, and some people think, why do we need to send our own? Well, that's because if you're sending data to a server, now presumably the server is also going to send something back, right? So if it's going to send something back, then of course it needs to know, what's our IP, right? So what's our like return address effectively, just so it knows who to send it to. Right, then of course there's also going to be the destination IP. Destination IP, and again it's obviously kind of difficult to kind of write small on here. So here then, I mean, this is really going to be more A level, but again, I mean, you can also include this if you want. Now, there's also going to be a port number, right? So when we say ports, let's say if you send data to a computer, actually, obviously that's based on the IP address. Now, the thing is, when your network card receives it, actually, it doesn't know what process to actually forward that data onto. Right, because let's say, I don't know, you've got sort of Chrome open in sort of one thing, then maybe you're also playing a game, right? You've also got, I don't know, say like sort of Outlook open, you've also got some torrent program, right? Just sort of obviously various things all using the internet at the same time, right? So actually each of those is going to have a different port number. So that's kind of why we need a port number, right? Okay. So just so, well, basically the network card then knows, well, if for example we get the port number, I don't know, 5000, well, 5000 is, let's say, tab 1 in Chrome, right? Then of course it will forward it onto Chrome, and obviously Chrome then knows, well, what sort of tab that's for. Right, let's say if it's 5001, well, that's, say, tab 2 in Chrome, right? If it's 5003, right, that can be, I don't know, some online game you're playing. Right, so hopefully that makes sense. Kind of what a port is. It's basically just like an ID number specifying the process that you're trying to communicate with. Right, and actually if you're talking about servers or different protocols, then there are actually some common ports, right? So some common port like 80, well, that's going to be HTTP. Right, if we have 443, right, so 443, well, that's HTTPS. I think is it sort of 21 and 22. So I think there maybe FTP. I think maybe FTPS. Right, so the file transfer protocol. I think maybe SSH, right, the secure shell. So logging into a server. That's also something like that. Although I've kind of forgot that one. Okay, let's kind of say that, right. Okay, so here then, well, again, that's going to be the source. The source, right, port. Then we have the destination port. All right, and then I guess just a few more. So here then, probably one, we can say is the length, right? So this is the length of the data, right? And the reason that's used, one is used, I guess, just so the receiving device obviously knows when the data ends, right? Just so it knows, this is the end of the data, and then obviously the remaining stuff, that's the trailer. All right, because if we think everything is binary, so we need to actually tell it how many bytes of data there are, just so it knows kind of when to split. Right, so let's kind of say that. Let's say I know what packet length. All right, and then I'm just going to do one more. So we can also say the sequence number. All right, so when we say the sequence number, that's basically the packet number. All right, because again, if we think if we have a big file, that file of course gets broken up into packets. Now what we're then going to do, we're then going to attach a sequence number, right? So of course, packet 1 gets the sequence number 1, right? Packet 2 gets the sequence number 2. Packet 3, right, gets the sequence number 3, etc. All right, now I think actually in reality they are given some random offset, just for security purposes. But that's kind of another thing. All right, but it's basically kind of given an order like that. So then what happens? Well, then the receiving device, if for example it gets packet 3 and packet 1, well then it's going to realize, actually it hasn't received packet 2. Right, so of course, then it can, for example, ask for packet 2 to be resent. Right, and also it's obviously going to be used for ordering. So if it gets packet, say 3, then 1, then 2, then of course it knows how to reorder that, right, 1, 2, 3, just so of course it can then process the data, kind of in the correct order. All right, so I think that's also going to be kind of what we want to draw here. So we're probably going to have, let's say multiple different networks. We can then have, let's say some routers in the middle, the packets going between them, and then I guess also the packets being reordered at the end. So let's kind of do that. All right, now I think usually for a router they sort of draw it as a circle. So let's say, I don't know, router. All right, and let's sort of give that some IP address. I don't know, let's say 111. Right, let's go 111. We'll just go sort of 4 groups of 1 like that. All right, and then let's also say that's connected. We'll just go, I don't know, some PC. So let's say PC. All right, and this is going to be our private network. So let's give it a sort of private IP like 192. Let's go 168. Let's go .0 and then .1. Right, and I guess let's also just do another PC as well. Right, let's go PC, and again, that's going to be 192, 168 is on the same network. Let's go 0, and then let's go .2, because obviously here, if we've got a .1, right, here we've then got a .2. They obviously have to be unique. All right, so what I'm going to do, let's maybe just sort of draw some kind of dashed line around that. Let's say that's going to be our private network. All right, let's go private network. All right, now actually this, 1 sort of 12 ones, right, that's actually going to be a public IP. Right, now actually if we think, the router, that's going to have both a public IP and a private IP. Right, now the private IP, that's used, let's say, when the PC is sending data to the router, right, and also, when the router is sending data back to the PC. I guess sort of not really on the return journey actually. All right, so it's sort of just used when the device is sending data to the router. Right, however, the public IP, that's then used, of course, when people from outside the network are sending data into the network. All right, so let's just sort of do here, I don't know, let's say routers. Right, let's say, I don't know, sort of like global internet. All right, so yeah, global internet. All right, so what we can, and again, this is going to be quite, yeah, quite difficult to draw because, well, I've not really given myself much space. All right, but what we can say, let's say, I don't know, some like video file, or I don't know, some, yeah, sort of big data. All right, so let's go video file. All right, and then what I'm going to do, let's sort of say, I don't know, it's kind of split into packets. I say, well, video file split. Right, I don't know, yeah, split right into packets. Right, split into packets, right, and sent. All right, so then what's going to happen? Well, of course, they're then going to be sent along here. All right, so all right, okay, let's maybe number these as well. Let's just do that in green. All right, so let's say here, well, this is packet 1, that's packet 2, that's packet 3. Now, let's say, for example, let's all go back to that orange. All right, okay. So here then, let's say, I don't know, this is like packet 3 maybe. And then I guess maybe we can do something else. Maybe packet 1 can go along here. And yeah, let's kind of do another one. All right, so let's say maybe that can go to there. Now, let's say here, maybe there's some error, right? That's, yeah, some like, I don't know, some like network error. All right, and then let's kind of sort of draw this here, go into the server at the end. Yeah, let's kind of write that. Let's say, I don't know, like web server. And I don't know, well, let's just give that like 222, right? 222. I guess, yeah, 222, right, and 222. All right, so here then, well, that's going to receive the packets. And yeah, let's just sort of do that. I mean, this is quite a detailed diagram. It's, yeah, well, maybe more detailed than you need. Yeah, again, it's sort of, yeah, probably faster if you're just doing it with a pencil. All right, so let's kind of do that. Right, okay, let's say here, I don't know, maybe this is like, say, 3. Oh, all right, okay, yeah, okay, right, okay, let's go 1. Maybe that can be 3. Right, let's go 1. Let's go 3. And then let's actually just sort of erase this. Let's say maybe here, yeah, for I don't know, for some sort of weird reason. Well, let's say maybe packet 1 got sent along this route or something. Yeah, just for some weird reason. All right, so yeah, okay, let's do that. Right, let's go packet 1. Then I guess, well, packet 1. All right, so let's say here, well, that can be, for example, packet 3. That can be 1. That can be 1. Right, okay, yeah, let's all do this in blue. Right, now what we can say, let's say what packet 1, or okay, well, let's say, right, packet 3 arrived. Right, so packet 3 arrived, right, then packet 1. Right, then packet 1. Right, well, let's say what, so, right, so server, or what, yeah, okay, let's say so web server, right, will have to reorder them. Right, have to, yeah, okay, well, right, just 1. All right, have to reorder them. Right here, well, let's also mention packet 2. Let's say, right, packet 2. All right, packet 2, well, didn't arrive. Right, didn't arrive. Hence will have to be resent. Yeah, hence will be resent. Yeah, I know, well, resent on the network. All right, so hopefully that makes sense. I mean, again, it's like super messy handwriting. It's definitely not a good diagram. All right, but again, hopefully the hopefully the diagram and explanation does kind of make sense. Right, okay, then a couple of empty pages. Right, so 5A, student stores their schoolwork on secondary storage devices. They store their schoolwork on their home computer, right, and also on cloud storage. So we want to give 2 characteristics of secondary storage. Right, okay, so I think the first one, well, we can say is going to be non-volatile. Right, let's say, yeah, it's non-volatile. Right, let's say, well, meaning that data, right, okay, data, right, is retained. And yeah, even when the power is turned off. All right, so hopefully that makes sense what that means. Right, then the second one, and yeah, this is kind of a bit more difficult. All right, now you could say, well, generally it's going to be high capacity. I mean, they might accept that. I mean, it's not really very specific. All right, possibly they might accept that it's, you know, generally going to be cheaper than primary storage. Yeah, I mean, that's certainly true in the case of, for example, RAM. Right, now that's obviously not always true. I mean, I don't know, you could have some like super fancy secondary storage. I don't know, using some, yeah, like crazy, like, you know, new technology or something. But yeah, I guess that's why you say generally. All right, and then, well, you can also have, let's say, some primary storage that's cheap. Let's say you have some, like, you know, sort of like cheap like ROM chip. Yeah, just some really like primitive basic thing. Yeah, okay. So that's kind of something you could say. Now, I guess maybe you'd also mention, well, secondary storage can't be directly accessed by the processor, whereas if we say primary storage, well, that can be. Right, so I think I'm going to say that now. I think they don't always have that in the mark scheme, but I think they should accept that. So let's say, yeah, secondary storage. Secondary storage. Well, let's say data. Okay, well, yeah, okay, right. Okay, let's say data, right, stored, right, on secondary storage, can't be directly accessed, accessed by the CPU. Let's say, right, first it, has to, I don't know what, be loaded, be loaded, right, into primary storage. Yeah, well, primary storage, primary memory, right, such as, such as RAM. Then if we look at part B, it says the home computer has a magnetic storage device and the cloud storage uses solid state or flash memory storage. We want to complete the description of how magnetic hard disk drives, right, HDDs, and solid state drives or SSDs read data. We want to use terms from the list, right? Not all terms need to be used, and you should only use a term once. So let's just sort of read through these because I think often it's good to read through the keywords that we can use. Make sure we understand them. And then I guess it's also easier to fill in the blanks, right, when we know the possible options. So here then, well, when it says control, because they're talking about SSDs, well, then they're talking about control gates, right? So when we say a control gate, that's basically, the gate, right, the kind of electrical component, that the electric charge is applied to, right, in order to, open the, force electrons out of the floating gate, let's say to clear the data, right, or let's say to, to kind of like attract electrons into the floating gate, in order to write data. Right, so if you don't know about floating control gates, well, we'll look at a diagram in a minute. Okay, well, to electromagnetic field, I mean, I guess that's just physics. Right, so flow, I don't know, maybe they're saying flow of electrons, right, flow of charge. Again, talking about what SSDs, right, control gates, floating gates. Loss, right, so possibly that could be, I don't know, data loss. It could be, let's say, like electron loss. So talking about electrons leaking out of the floating gate, right? And that's also why they say that if you have a laptop or some phone, right, kind of anything using an SSD, then you shouldn't, for example, leave it off for, let's say, 2-3 years without turning it on, because actually what can happen? Well, the electrons can actually leak out of the SSD, right, and you're actually going to lose your data, right? So it's actually good, let's say, just to plug it in. Even if it's some 5-year-old laptop, right? Just plug it in, I don't know, once every year or something. Just for I don't know, probably just for like sort of 10 seconds will do it. Just to kind of recharge, recharge the electron sort of strength, or just kind of sort of top up the charge basically. So the next one, NOR gates. What if we think NOR? Well, obviously that's just a logic gate. Right, so OR, well, that's going to be 0, 1, 1, 1, right, as the output. When we say NOR, that's going to be, reversed or inverted. So that's going to be 1 and then, 3 zeros. Obviously, open, right, opened. Okay, right, pits and LAN, so I guess that's really talking about optical storage. So if you think optical storage, right, I've sort of drawn this here because actually I was recording the video then I had like a sort of power problem. My laptop just turned off. I think it was overheating. Alright, so I guess what I've done here, okay, right, so pits and LANs, what we can say, what you're going to have, well, actually the optical storage is not going to be completely flat. And this is going to be if it's the kind of write once. Now, actually, if it's read-write, where we can read and write many times, it's actually just going to be, it's going to be sort of changing the right, so like changing the reflection, basically, of the different parts of the disk. Using some laser to, basically modify the chemical structure, right? And what you say, if, for example, it's like a shiny part, because if it's like modified the atomic structure to make it into this kind of lattice which is shiny, then, for example, maybe that can correspond to a 1, right? If it's use some different frequency laser, let's say to, I don't know, change the atomic structure in a way that it's not a lattice, well, then it's not going to be shiny. Then of course that can, for example, correspond to a 0, right? So it's kind of the same thing here with pits and LANs. Right, so if we say a land, well, that's going to be basically a raised part of the disk. If we say a pit, well, that's actually part of the disk that has actually been physically burnt away, right? So there's actually no way to recover this because, again, we've actually physically burnt away some of the material. So that's why, again, this is going to be, well, kind of write once. Yeah, we can't really write it again, right? Because I guess, well, even though technically we could actually sort of, well, we could like obviously change this land, let's say here into a pit, for example, but we're not going to be able to change a pit back into a land. All right, then actually what we say, I think the way this works, it's not a case of, well, if it's, say, a land, it's a 1, if it's a pit, it's a 0. It's actually based on when it changes. So, okay, let's say here, well, let's say we have a 0, right, then another 0, because it's not changing, right, another 0, another 0, another 0, right, okay, but here, right, then it goes, well, from a land, right, down to a pit. So when we have a change, well, that's when the values then change, right, so here, then we have a 1, right, then of course we're still in a pit, we have another one, right, we're still in a pit, we have another one, obviously another one, etc. Right, so okay, here we get the final one in the pit, right, then we obviously go back up to a land. So because it changes, well, that's why again it goes from, you know, sort of 1 to 0, or yeah, obviously 0 to 1 depending on the scheme. Yeah, okay. So I think that's kind of what they're saying for pits and lands, right? Then platters, that's basically the individual disk in a hard drive, right? And I think a lot of people, and well, also me as well. I mean, I also thought that a hard drive just had, you know, one disk, right, one platter, but actually there's actually many different platters. I think some hard drives can be up to like 8 or 16 different platters. All right, and I think they also have data on both sides, right, both the top and bottom. Okay, right, ports. Right, okay. So ports, I guess really there's two types. Now, if you're talking about a hardware port, let's say like a USB port, or Ethernet port, well, that's of course the physical place where you plug the cable in. Right, now, if they're talking about a software port, well, again, that can be, well, for example, networking, right? That's going to be basically some ID. Which is kind of, well, used to represent a process. All right, so that's when, well, the network card then knows, right, forward the data on, you know, to the process with this port, just so it can forward it, well, to the correct program, right, the correct running process. Right, next, well, then just remove, right, and then obviously sectors, so that's going to be part of a platter. Now, I think in particular, a sector, that's basically going to be, I guess you'd say, some kind of angle of a track, right? So when we say a track, that's basically like a ring around the platter. Yeah, we'll see a diagram in a minute. Then, well, XOR, okay, well, that's again, that's another logic gate. All right, and I guess we can say, well, when the input is the same, the output is going to be 0. So let's say 0, 0 goes to 0, 1, 1 goes to 0. Right, when the output is different, well, then it's going to go to 1. All right, and yeah, okay. So if you want to think of a specific example, let's say a real life example, let's say you say on the weekend, well, either I'll, you know, say go and watch the football, yeah, let's say X, or right, I'll watch the basketball, because if these two things are happening at the same time, well, then of course you can only do, right, one and only one of them, right? You sort of can't do both of them, right? So that's where it's going to be different to an OR, right? Because, well, OR, of course, we can do both of them. But yeah, XOR, well, that's kind of, yeah, only doing one of them, right? And I think actually, probably in real life, probably XOR is actually more common, right? So when someone says, I don't know, you know, what, do you want to eat beef, right? Or do you want to eat, you know, say pork? Well, really, they actually mean XOR when they say that, because, yeah, presumably they're not going to give you both on the same plate. All right, so that's kind of, yeah, quite commonly used in real life. Yeah, probably the default really for. All right, anyway, let's sort of go to the go to the diagrams here. Okay, right. Okay, so right here then. Well, these are obviously two diagrams for the hard drive. Now, I mean, this is really just showing the physical layout of it. So if we look at the first one, well, when it says track, and in fact, all right, okay, let's maybe start. Yeah, hang on, what's happened there? Okay, let's maybe start down here on the platter. Yeah, where is the mouse? Okay, there we go. Okay, right. So here then, okay, right. So the platter, well, that's basically the entire disk, right? And if we look, well, here we've also got what sort of platter 1, platter 2, platter 3, right? So in this, obviously, well, sort of part of a diagram, right? They've obviously shown 3 platters, right? Okay. So here, then we say track. So when we say track, that's basically, well, that's kind of, let's say, like the radius, yeah, around the hard drive, or well, kind of around the platter. Right, so here, well, this is, let's say, track 1. Right, then, for example, if we have, let's just go out the radius a little bit, or well, just sort of increase the radius a little bit. Right, this, for example, is going to be, let's say, track 2. Right, then if we sort of make the radius a little bit bigger, right, that's obviously going to be track 3. And so obviously, yeah, kind of difficult for me to draw on this. then obviously we go out, right, track 4, track 5. All right, so let's just sort of number that. Okay, let's say this is right, track 1, right, then obviously we have track 2, track 3, track 4, right, track 5, etc. Yeah, just kind of going, increasing the radius outwards. All right, so that's also going to be related to the cylinders, because what we can say, okay. So here then, what is cylinder? That's basically like the corresponding vertical track, on all of the platters. So let's say, for example, if we're reading from track 1, now because if we look at the arm, well, again, this is just like a singular thing. So because this is a singular thing, then actually whatever track this is reading, let's say on platter 1, well, it's also reading the same platter. If we look, it's reading the same track, right, on, platter 2, right, it's also reading the same track on platter 3, platter 4, because again, it's all just like one arm. It's all just like connected. All right, so that's kind of what they mean when they say a cylinder. They're saying, well, this, for example, would be cylinder 1, because again, obviously we're sort of track 1 here, right, we're track 1 here, right, and also we're track 1 here. All right, so if they're saying, we're reading data from cylinder 1, well, that means obviously reading data from sort of track 1 in all of this, on all of the platters simultaneously. Right, now possibly you can think, let's say you have I don't know, some large file, let's say some video or some massive like archive. Now if you think, well, would it be a good idea, let's say, to store the data, right, maybe some of the video here in track 1, let's say the next part of the video here on track 5, right, the next part on track 3, right, hopefully you can realize that that's not going to be a good idea, because actually what that means, well, the read write head has to keep moving location, so that's actually going to be quite slow. What the arm has to sort of go in and out all the time to move the read write head, right, which I guess we can sort of see here a bit better. Here we go. Obviously just sort of moving this read write head, kind of like in and out like this, just so it can go back and forward to different tracks. Alright, so actually a kind of better option would be, well, what we can actually do, we can split the video or the large file, and we can basically store it on, let's say kind of the same track, right, but obviously on different platters, right, so we're storing it on the same cylinder, right, so let's say, I don't know, let's say here, right, this is like part A of the video, right, part 1 of the video, let's say this is like part B of the video, right, let's say, again, this is obviously, part C, or let's say like the end of the video. Right, so because we're storing all of this all on track 1, right, so the same cylinder, right, but obviously different platters, well, then we can actually read all of that consecutively, right, we can load all of that into RAM at the same time, right, of course that's going to be much faster. Alright, and then so here then, obviously the spindle, well, that's just the actual physical thing in the middle that the platters are connected to, right, it's actually spinning around, right, and then I guess also here again, that's kind of the same diagram. I'm not going to explain it, but of course, hopefully you can understand what that's showing. I guess sort of pause it, right? Make sure you do understand all of that. All right, then if we move to the next thing, SSDs. Right now, I think a lot of people get confused about this, but I think if you look at the kind of basic principle, it's actually not that. It's kind of not that difficult, hopefully. All right, so what we have a control gate. Now, basically, the control gate, well, we can kind of like apply a charge to this, or sort of like a voltage. Right now, either that can be positive or that can be negative. Right, now if we look here, this floating gate, well, this floating gate, that's basically this blue area, right, and the reason it's called floating, that's because it's not connected to anything. Okay, so above this, you have this oxide. Right now, the oxide, that's basically like an insulator, right, so because we have this, well, then it means that the electrons, here then, right, so these electrons, well, because we also have this oxide at the bottom, right, these electrons are sort of not going to go through that, if we don't have any charge, right, so the default state, well, the electrons are not going to go in, into the floating gate, right, and also when they're in the floating gate, well, the electrons are also not going to leave the floating gate, right, if we have no charge. Right, however, what we do want to do, well, we do actually want to move them. So if you can think about that, you sort of want to think, what charge would we want? Right, so let's say here, well, because we have the, and again, where's the pen? Okay, right here. Okay, so here then, if we have a negative charge at the bottom, now if you think, well, what charge do we want to apply to the top, right, either, positive, right, or negative, in order to get those electrons to move up, right, so hopefully you realize, well, if we apply a positive charge, well, then what that's going to do, because obviously here we've got positive at the top, negative at the bottom, well, that's then going to cause those electrons to move up, right, into this floating gate. right? So that's going to be while writing data, we're obviously setting data, right? Then if we want to remove data, or obviously while sort of reset it to 0, well, then we want to think, okay, yeah, that's obviously the second diagram. Okay, so here we've got a negative charge in the floating gate. So then we think, well, what charge do we want to apply, right? Positive or negative, to get these electrons from the floating gate, well, back just here into the, into the kind of, just sort of like, I don't know, sort of like sort of resting area. The sort of drain. All right, so what we can say, I mean, hopefully it's fairly obvious. All right, so what we're going to do, well, if we apply a negative charge, obviously negative, negative and negative, they're going to repel, right? Therefore, that's obviously going to force these electrons down, all right, out of the floating gate, and again, well, back into this, back into this kind of storage area, which I'm actually sort of not sure what they would call this, but yeah, I think we don't really need to know. All right, so hopefully we can then use that just to sort of fill this in. Okay, right, so the paragraph for a hard disk has several platters. Right, each platter is split into tracks and right. So here then that's going to be sectors, and I think we actually didn't really mention that. Right, so if we look at a sector, basically that's going to be a part of a track. In fact, let me just kind of undo all of this because I've sort of written over it. We can't really read it. Okay, that's kind of annoying. Let's just erase this. All right, okay, let's sort of do it here. All right, so I think actually, here then, so we can actually see it says sector, right? So what that's really saying, that's just going to be part of the track. So let's say this track. Well, here we also have sector 1, sector 2, right, sector 3, 4, 5. All right, so kind of each of these individual, let's say blocks of data, right? Well, that's going to be considered a sector. Right, now I think also hard drives, well, they're also split into blocks. Now I can't remember if a block is bigger than a sector or if a sector is bigger than a block, right? But again, it's basically going to be the same thing. So if you're, let's say, reading or writing data, well, you can't, for example, just read one individual bit, right? You have to read like an entire sector, or maybe an entire block at a time. So that's kind of what that represents. It's kind of about how much data and how much data you're reading, right, and writing to at the same time. So yeah, let's kind of write. Okay, right. So each platter is split into tracks, and sectors. Right, to read data, the read-write head moves over the platters to the position where data starts. Right, the something indicates if the data is a 1 or 0. All right, so I guess for that, well, we would say the electromagnetic field. All right, so yeah, kind of really just based on the polarity, right? If it's positive, if it's like a positive magnetic field, right? If it's a negative magnetic field. So let's just go ahead and write that, right? Electromagnetic field. Okay, then the second one, right? So a solid state drive using NAND gates, right? Or, well, that's going to be NOR gates, right? Because actually, if we think, well, I mean, one, maybe you just remember, right? Flash memory is NAND and NOR. But also, well, NAND and NOR, they're also considered what's called universal gates. So when we say a universal gate, right, and you can sort of search this if you want, basically that means, from a NAND and NOR gate, we can actually make all of the other gates, just from, NOR gates, or just from NAND gates, right? So let's say, for example, an XOR, we can say an XOR, that can be equal to, obviously, some combination of, NAND gates, or, some combination of NOR gates. Likewise, obviously, and or not, XNOR, right? So all of those other gates, again, they can be made, right, just from NAND or just from NOR. Right, so yeah, hopefully that kind of makes sense, what I'm saying. Right, so it is made of transistors that work as, floating gates, right, and something gates, right? So that's going to be control gates. So again, remember control gates, either we apply a positive or negative charge, just to get electrons to go up into the floating gate, and then obviously, back down, kind of out of the floating gate. Right, so the gates control the something of electrons to memory cells. So I think here, that's like we said, flow, right? So yeah, the flow of electrons to memory cells. Alright then, CI, so we want to state what is meant by cloud storage. So hopefully that's going to be a bit easier. Right, what we want to say, basically it's going to be, remote storage. So I guess, storage kind of, stored in a different location. Right, let's say that, right, the provisioning, I think that's the word they like. Alright, the provisioning, right, let's say of remote storage. To store your data. And let's kind of maybe explain what remote is. The provision of remote, let's say, right, at a different I know, yeah, at a different geographical location. Yeah, I think that's sort of fine, really. All right, and I guess you could mention it's what usually hosted by another company. I guess you could also have a private cloud, which yeah is just for you, or yeah just for your company, right? But I think usually it's often going to be what a public cloud, something like what AWS or Amazon Web Services, yeah I guess what Google Cloud, Microsoft Azure, yeah kind of all of those. Right, okay, then two, we want to explain the advantages to the student of storing their data on cloud storage instead of storing the data locally on their home computer. Right, okay, right, 2 marks. So let's see if we can think of all of them. Right, now I think the first one, a cloud storage, well, one, you can basically use it on any device. Or yeah, you can access your data from any device. Right, so if, for example, while you're storing it on your computer, well, then let's say you want to access, the device on your phone. I mean, I guess it's possible what you could I don't know, let's say you have some, sort of messaging app, right? You could send it to yourself on a messaging app. I guess you could plug in a USB cable, transfer it, right? But still, that's possibly a little bit sort of, tedious, right? So I guess if you're using cloud storage, well, obviously you just, connect all to the same storage. Yeah, you can access your files from any device. So let's say that, let's say, I guess, seamlessly. Okay, let's say, right, the student, right, okay, can easily access and edit their files, I guess, yeah, on any internet enabled device. Let's say right on, yeah, okay, on any device, right, with internet access. Right, okay, so that's going to be one, right, okay, so let's say two, we can probably say, well, basically there's unlimited storage. Yeah, okay, right, let's say maybe unlike, yeah, all right, okay, well, let's say, right, unlike, I know, yeah, her laptop, or yeah, I know, her device, which, right, has limited storage. Right, okay, well, all right, let's say, right, big cloud companies, right, have effectively unlimited storage sizes. Yeah, okay, right, okay, so is there anything else? So, right, what's the benefit of storing it remotely? All right, so I think we can also mention about backups. So you want to say, well, if it's a remote backup, then let's say there's some problem, I don't know, maybe in a location, right? So either that could be some kind of natural disaster, right? Maybe there's an earthquake, there's a flood, there could be a fire, right? Let's say all of our, computers, phones, they all get destroyed, right? It could also be, let's say, like a burglary, right? Someone breaks in or someone steals her bag, right? Well, obviously a laptop or phone inside, right? So if we're also, sort of storing it on the cloud, well, then we're actually storing the data in two places. So even if, there's a fire in your house, well, because obviously you're storing it, in some other city in the cloud, well, then of course, right, that data is going to be safe. So let's say the cloud, right, can operate, right, as a remote backup. Let's say you were in a different, in a different city, right, / country. Right, okay, let's say hence, providing, I guess, safety. Right, safety, maybe let's say against data loss. Yeah, well, okay, let's say, I don't know, due to like natural disasters. Right, natural disasters, I mean, even like wars, yeah, you could say crime, yeah, I guess, etc. All right, and I think, yeah, okay, so here then, even wars, I mean, this is also quite relevant. So I think if you think, let's say, like during, when the Ukraine war started, now there's actually quite a lot of people had, servers in Ukraine. I mean, maybe not necessarily for, legitimate purposes, but I guess especially some kind of, yeah, possibly, slightly nefarious purposes, right? Some like hackers or something. So if they had servers in Ukraine, well, then of course, kind of when the war started, well, I mean, those companies, I mean, possibly they just either just all went bankrupt. Yeah, I mean, or what the employees left, right? The employees were obviously drafted into war, so that then of course, right, all their data is going to be lost. So yeah, that's obviously why it's again, good to back up in, let's say, multiple different countries. Yeah, if you're some big like serious company. Right, okay, 3. So then we want to explain the advantages to the student of storing their data locally on their home computer instead of using cloud storage. Okay, right, yeah, okay, right, okay. So here, again, let's try and think of 3. So 1, you can say privacy. They're not sending their data to some, other company. 2, we can say speed. because, well, I guess what is obviously going to be faster. You're not having to transmit data over the network. Yeah, you're just directly loading it from your SSD, right, or directly loading it from your hard drive. Right, then I guess also 3, well, we can use it even without internet access, right? And I think also 4, we can also say, well, it's going to be cheaper. So even if you're talking, I don't know, let's say you've got like a couple of terabytes of data, now realistically it's kind of much cheaper just to buy, let's say, like a 2 terabyte SSD, rather than paying for 2 terabytes of cloud storage every month, because what the initial one-time payment is going to be much cheaper, let's say after like 2 years, yeah, rather than buying that 2 terabytes of cloud storage. So yeah, let's try and say some of those. Let's say the student right, maintains their privacy, right, since the data right, stays locally, or well, yeah, stays local, right, rather than, I don't know, possibly being inspected right, by the cloud company. Yeah, I think that's fine. Right, let's also mention internet access, right? Okay, also the data, yeah, I guess, yeah, the data can be accessed, right, accessed without internet. Yeah, I guess let's also say, right, let's say and at faster speeds. Okay, well, let's say, right, since I don't know, yeah, since loading, right, data from secondary storage, well, let's say, yeah, is much faster, right, than transmitting data over a network. Well, yeah, right, transmitting data over a network. Right, okay. So then let's say finally, and let's mention the price. Finally, let's say what making one-time payments. Let's say, I don't know, for large secondary storage devices, right, will be much cheaper, right, than storing. Okay, all right, okay, yeah, all right, okay. Let's say much cheaper in the long run, right, much cheaper in the long term, right, than, let's say, paying monthly, right, for a large amount of cloud storage. Yeah, okay, right, so I think that's fine. Right, then 6, we want to convert the denary number 150 into an 8-bit binary number. Okay, so if we think, well, 150, now because we're only using 8 bits, right, this means it must be unsigned, because what the biggest signed, the biggest signed number, or the biggest 2's complement number that we can represent with 8 bits is going to be, well, obviously 127, right, because, well, the range minus 128, right, up to positive 127. Right, so what that means, well, the most significant bit, that's going to be positive. Okay, so let's just write these out, right? Okay, so that's going to be 128. Now, if we think 128, of course, there's going to be a 1 here because, well, 150 is bigger than that. Right, then we're going to want to make 22. So if we think, well, 64, there's not going to be. I guess, yeah, 32, well, there's also not going to be. Right, then if we think 16, well, there will be a 16. I guess if we think 8, right, there's not going to be because we need just 4 more. Okay, no, sorry, 6 more. All right, so let's go 4. Well, there will be a 4. Right, there will be a 2, and okay, yeah, there won't be a 0. All right, so what I'm going to do, well, let's just show our workings, or just kind of add those up. So let's go 1 to 8, and I guess just to make sure we haven't made a mistake. Right, then go 16. Let's go 4, and we'll go 2. Right, so if we add this up, well, 8 plus 6, that's going to be 14. I guess, well, plus 4, that's going to be 18 plus 2. Well, that's going to be 20. So let's carry the 2, and then 2 to 1. Right, that's going to be 5. Then obviously, well, 1. That's going to be 150. All right, so I guess here, well, then, of course, we want to write down the binary number. Right, okay, then B, we want to convert the hexadecimal number F08 into a 12-bit binary number. All right, so this is quite easy. Now, I think some people, sometimes they get confused. I don't know, they try to convert it to denary first, then from denary, they go to binary. Now, that's going to be quite difficult. Right, so actually instead here, what we think, well, 1 hexadecimal digit is going to be equal to 4 bits. All right, so what we do, and well, that so here then that's because of this rule. Right, so 2 to the power of 4 is equal to 16. Right, so what we're saying, well, 16, right, that's 1 hexadecimal digit, right, 16 different combinations. Well, that's going to be equivalent to, well, the power of 4, and obviously using 4 bits. Right, so yeah, 4 bits in base 2. Right, is equal to, well, 1 bit in base 16. Right, so all we have to do, we have to say, well, the F, right, treat that as 4 bits, the 0, treat that as 4 bits, 8, treat those as 4 bits. Right, so if we think F, well, F is just 15, so that's what 4 ones, well, 0, of course, that's 4 zeros, and then 8, well, that's a 1, and then obviously 3 zeros. right? Because again, obviously just going what 8421, yeah, 8421, or obviously 8421, yeah, just for those 4 bits kind of independently, yeah, for each of those nibbles. Right then, C, we want to give the 8-bit binary value after a logical binary shift left of 2 places, right, is performed on this binary number. All right, and also actually just to go back to part B, right, now we can also do the reverse. So let's just say, I don't know, we just have some number, let's say like 1100, let's go 0011, right? Now if they say, well, this is some binary number, right, convert this to hexadecimal, well, all we do, we take obviously these 4 bits, well, that's going to be a 3. Then we take, well, these 4 bits, right, that's going to be 12. So if we think, well, 10 is, well, yeah, okay, so right, well, A is going to be 10, right, therefore 12, that's going to be C. All right, so hopefully it makes sense. So obviously hex to binary and binary to hex. Yeah, it's just really simple, right, treat them as 4 bits. Right, okay, right, so here then, doing this logical shift. So what we want to do, now, okay, some people do actually move them up, so they do think, well, this one goes obviously 2 to the left, this one goes 2 to the left, this one goes 2 to the left. Now, that is one way to do it. It's actually quite slow, right? I think actually a better way to do it, well, what you think, because it's a logical shift, so we don't have to worry about like keeping the sign the same or anything. What we can do, well, we can basically just cross out those, right? So of course this is going to be the start of our number, right? Then we just write 2 zeros on the end, right? Because that's kind of what's happening. We're shifting out the 2 first bits, and then obviously just adding on 2 zeros at the end, right? So if we then just want to write out the whole thing, and then I think, yeah, okay, that's going to be 8 bits, just making sure I haven't missed any. Then D, we want to convert the 2's complement binary integer into denary. Alright, so when it says 2's complement, remember, well, that of course, okay, yeah, okay, right, okay, so not -1, right, it just means negative. Right, now I guess in this case, because we're using 8 bits, well, that's minus 128. Now here, actually, because this is a 0, well, we're actually not having any negative number, it's going to be positive. So, well, this is going to be the same whether it's signed or unsigned. Yeah, we've got no negative value here. All right, so hopefully we can do this quickly. So what do you think? Well, this, of course, is going to be the 64. So let's go 64 right then. Obviously, we've got the next one, that's 32. Then we've got the, well, that's going to be the 16. Right, then obviously here, well, there's no 8, right? There is a 4 and also there is a 1. So let's go 4, let's go 1. All right, and if we add these up, right now, I've actually done this before. So our 4 plus 2 is 6, plus 6, right, that's going to be 12. Plus 4 is 16, right, plus 1, that's 17. Right, then obviously carry the 1. Okay, here, well, 1 plus 6 is 7, plus 3, 10, right, plus 1, that's going to be 11. Obviously carry the 1, right, that's 117. Right, and actually we can sort of check that because this sort of does work. Right, now if okay, right, so here then, if we think, now if we have these 7 rightmost bits, now what that's going to equal 127, because, well, that's the biggest number we can represent with 8 bits 2's complement. Right, so here, because we've got 117, well, actually, if we look at this, well, here we don't have the 8, right, and also we don't have the 2. So if you think, well, 127, that's if they're all 1s, right, but here we have 127, well, and then obviously here, well, minus the 8, minus the 2, right, and that's going to give us the 117, right, so that's kind of a good way just to check our answer. Right, okay, then E, so we want to add the 2 binary integers using binary addition and also give our answer in binary. We want to show all of our work in. Alright, so hopefully we know how to do binary addition. If we don't, I mean, just quickly. Alright, so okay, let's go 0 plus 0. Well, that's going to equal 0. Right, sum of 0, carry of 0. Let's go, well, alright, okay, hang on, okay, let's undo that. Okay, let's go, well, 0 plus 1. Well, that's going to equal 1. Right, so what we're saying, basically, well, that has a carry of 0, and then, well, a sort of sum of 1. Yeah, okay, that's a terrible one. Yeah, okay, right, and that's also 1 plus 0, that's also 1. Right, now let's say here we have 1 plus 1, well, that's going to be 2. Now, if you think in binary, the way we write 2, well, that's going to be 1, 0. Right, so what we're saying, well, here then, the sum is going to be 0, and then the carry, right, that's going to be 1. Now, if we have, well, 1 plus 1 plus 1, right, if you think in binary, that's going to be 3. So what we're saying, well, again, it's going to be a sum of 1. Right, but it's also going to be a carry of 1, because again, well, 1, 1, right, that's 3 in binary. Alright, so that's going to be what we want to do. Okay, right, so here then, well, 0 plus 0 is 0, right, 1 plus 1, well, again, looking at our rule, well, that gives us a sum of 0, and then we'll carry of 1. Again, well, 1 plus 1, because obviously the 0 doesn't count. 1 plus 1, well, that gives us a sum of 0, right, carry 1, okay, yeah, carry 1. Right, here then, well, this is our 3 1s, right, so here we get a sum of 1, right, but we also get a carry of 1. And then here, right, okay, so, well, 1 plus 1, that's going to be, what, 0, and then a carry of 1. Again, obviously 2 1s, right, 0. Yeah, 2 1s, again, 0, and, well, obviously here, Right, okay, that's going to be the 1 1 like that. Alright, so here again, we should be able to check this. So let's just think what that's going to be in denary just to check. Okay, so here, well, obviously that's 128. Right, so this is going to be 16. That's 8. That's 24. That's going to be, I think, 26 if I've not made a mistake. Then here, well, that's 64. Right, that's 32. So that's 96. Then, well, that's 8. So 104. That's going to be 4. So 108. Right, that's going to be 110. Alright, so I guess we should be getting, what, 136? Okay, and I realise I must have done something wrong because, well, here then, that's going to be, well, that's going to be 128. No, okay, no, yeah, that's fine, right? Okay, yeah, okay, right. So 128, right? Then plus 8, and yeah, that should be the 136. All right, so I think hopefully that's correct. Okay, yeah, 7. All right, let's see how many more do we have. I guess, okay, right, not too, okay, yeah, all right, okay, there's still quite a lot actually. Right, let's try and go through these quickly. Right, so 7, data is transmitted between a computer and printer using a wired connection. The computer transmits the data to the printer transmits data and interrupts the computer. State whether the method of transmission would be serial or parallel, and we want to justify our choice. Alright, so let's get the thing. Right, okay, right, so here then, well, serial or parallel. Now, if we think serial, well, one, the advantage is simple. I guess it's also cheap, right? But in particular, the main thing, basically, it's going to be reliable, right? And also, it can operate over a long distance, if we're thinking about a wire, right? So if we have parallel, the problem with parallel, basically, we get something called skewing. And let's just sort of do this diagram, right? So let's say here we have like multiple wires, well, obviously, yeah, multiple parallel wires. Now, what can happen? Well, maybe let's say you have, one bit of data here sent at this time. Right, but then let's say here maybe this 0 is sent at this time, right? So they become obviously kind of unsynchronized, right? And obviously if this continues, well then they can get completely out of sync, and you could have a situation where let's say here, right, maybe we've received I don't know say like 101 bits, right? Whereas let's say on this one, well then we've only received 99 bits, right? So then obviously if we have this kind of situation, well then the data is obviously going to get all corrupted, right? So that's going to be the problem with parallel. And I think generally they say that generally I think this kind of skewing, this becomes a problem, even just with like a sort of 1 meter wire, right? So generally you don't want some 10 meter cable like this. Often that's going to create problems, right? Which is if you think, well, that's why actually most cables are quite short. And then I guess if you have a longer cable, well, either they're using serial transmission, or they've got some kind of other some kind of error detection that can obviously handle the skewing. Alright, so I think for this, I mean, we can probably then say serial. That seems probably likely because, I mean, if we're printing, I mean, we generally don't need some, super high data transfer rate. We're not sending like gigabytes and gigabytes of data to the printer. So yeah, let's say that, right, okay, let's go serial. Okay, right, so justification, again, probably 1 mark for this. I don't know. I mean, possibly 1 mark for the method, 1 mark for the justification. Right now, actually, they probably let us choose, I guess, either right serial or parallel. So it's actually probably 2 marks probably for the justification. So let's say right serial. Serial is reliable. I guess and simple. Right here, let's say it doesn't suffer from the problem of skewing. Right, let's say hence. Right, we are able to use long cables, I guess, well, without worrying about data corruption. Let's kind of say that, right? Okay, so long cables, let's say I know maybe between say office. So it sort of doesn't really say, but let's say I know between office, let's say home devices, and a printer. Well, without worrying. Let's close the bracket here. Alright, so without worrying about data loss, or data corruption. Alright, and then I guess we can also say it's probably sort of cheaper, and also, again, printing, it doesn't require a super high bandwidth. Alright, okay, also serial transmission, is cheaper. And since let's see since we don't have to send huge amounts of data to the printer. Since we don't have to send gigabytes. Let's see, gigabytes, right, of data, right, to the printer, I don't know, yeah, per second. Well then, right, serial, I know, yeah, serial transmission, yeah, is, you know, fast enough. All right, so I think that's fine. Okay, right. Okay, then B, we want to state whether the method of transmission should be simplex, half-duplex, or full-duplex. Right, and again, just for our answer. Right, so I think here probably we want to say full-duplex because, again, I guess similar with the drone, we probably want data going back and forward in, well, two directions simultaneously. Right, so if we think simplex, well, simplex means only in one direction. So I guess you could say, well, only from the computer to the printer. Right. However, you wouldn't really want to do that because really the printer should also be sending messages back. So that can be some kind of some kind of interrupt, right? Some kind of error. So some errors, well, maybe the printer is out of ink, the printer is out of paper. Right. I guess you can also say, what if the printer is finished? It can send like a successfully printed message, right? And probably also there will be some kind of back and forward. Just for example, telling the telling the computer, let's say, to slow down, right? If it's sending too much data too quickly, yes, there's going to be some kind of I don't know, some kind of let's say communication, yeah, just so it doesn't overwhelm the printer with too much data. Alright, so I think you wouldn't want to use simplex. Right, you probably also don't want to use half-duplex because again, that means only one can send data right at the same time. So let's say if you have, I don't know, the printer sending something, right, but at the same time we all, okay. All right, okay. So let's say we have the computer which is like sending some files to be printed, right? Then at the same time we would also want maybe the printer to be sending some status message. Again, what printer out of ink, right? Printer, I don't know, yeah, printer out of paper. All right, so I guess in that case, well, that's why we need full duplex, right? Since we can send both of those simultaneously. Right, okay, justification. Let's say, I don't know, yeah, full. Well, okay, right. Let's say since. All right, since this allows data, I don't know, yeah, data, right, slash interrupts. Yeah, interrupts to be sent. I guess what in both directions. Well, let's say, right, yeah, between the right, computer and printer simultaneously. All right, and then I think if we just give examples, so like the ones we said. Yeah, I've spelled simultaneously wrong, but again, never mind. Let's say, for example, the computer, right, could be sending documents to be printed. All right, let's say while the printer. Right, okay, the printer maybe, I don't know, yes, simultaneously, right, sends, let's say sends an interrupt, well, let's say, right, notifying the computer to stop sending, right, the computer, right, to stop sending, well, I don't know, yes, since the RAM is full, or since the print buffer is full, right, since the print buffer, yeah, is full, I don't know, yeah, the printer is out of paper. Right, out of paper, right, ink, etc. Right, okay, then C, so the transmitted data may contain an error. Give one way in which an error can occur during data transmission. Alright, so I guess for this, I mean, probably we can say some hardware error. Yeah, maybe there's, some error like with the actual physical wire. Right, I guess we can also say what interference. So that could be a kind of electrical interference if it's on a wire. I guess if it's, let's say, like Wi-Fi, well, then, of course, it could be what kind of radio wave, yeah, kind of what EM interference, right, kind of electromagnetic interference. So let's probably mention that, right, that's probably more common. So let's say interference could occur, yeah, let's say, right, on both a, on both a wired, right, connection, let's say maybe nearby, right, electrical, I guess, or electromagnetic, right, magnetic, right, let's say signals, what from nearby equipment, right, yeah, or like wireless, let's say, right, or wireless interference, I don't know, yeah, if lots of devices, right, are communicating simultaneously, lots of devices are communicating, let's say simultaneously, right, on similar frequencies, yeah, on similar, right, or the same, right, slash the same frequency. All right, because if they have different frequencies, well, hopefully then we shouldn't get interference. Yeah, there's also kind of algorithms used to, you know, kind of filter out any background noise like that. Okay, right, okay, then 2, right, so the computer and printer agreed to use, well, automatic repeat query, or, yeah, ARQ, right, and I think also they call that, well, automatic repeat request. Yeah, I think I've seen maybe 2 different names for that. Okay, right, okay, so then what we want to do, we want to explain how ARQ, using negative acknowledgement, is used to establish that data received without error. All right, so actually, I've sort of got a good definition here in the book. They explain it quite well. All right, so what they're saying, we're in a negative acknowledgement method. So looking here in the bottom right, the sending device transmits the first data packet. All right, then the receiving device receives the data packet and checks it for errors. So if the receiving device detects no errors, then no further action is taken. However, if the receiving device does detect an error, well, then it will send a negative acknowledgement back to the sender, right? And actually, the way it detects the errors, I guess it could be a checksum, right? Apparently, more commonly, well, again, it's just a CRC, right? A cyclic redundancy check, basically counting the number of ones, right? So, I mean, that's quite a kind of primitive method. But yeah, I guess that's kind of the most primitive method you could use, right? There's, yeah, possibly, you know, more complex methods, yeah, depending on, you know, the particular protocol and things. Yeah, okay, so I think that's fine. All right, so if there is a negative acknowledgement, well, then of course it means the data was, well, received incorrectly, right? Therefore here, well, the sender has to then resend that. All right, and also, well, finally, a timeout is also set by the sending device. Well, this is when it initially sends the data. This is just so that the sending device knows that if it doesn't receive a negative acknowledgement within that set time period, then basically it can sort of consider that as being successful, right, and then can send the next data packet. Right, now actually, I mean, this is okay, so this is not some kind of hard and fast rule, because you do have like many different protocols and many different implementations, right, and there are actually some kind of problems with just doing this. So let's sort of try and draw a diagram. If I can actually go down on this thing. Okay, there we go. All right, so basically what it's saying, let's just sort of draw this. Okay, right, this is, well, the sender. Obviously here, right, this is going to be the receiver. All right, so what's going to happen, and let's sort of give it a clock, right? Let's say, well, this is obviously 0 seconds. Right, now what's going to happen? Well, this sender is obviously going to send something to the receiver. Now, if the receiver receives it and there's no error, well, then nothing's going to happen. All right, and let's say we've got a timeout of, I don't know, sort of 0.2 seconds. So if there's no error within, you know, say 0.2 seconds, well, then it can then send what's sort of like kind of like the next packet. Right, now obviously if it's just waiting purely for the timeout, well, that's actually going to be extremely slow. So I think in reality, a lot of these, they'll send kind of like multiple packets all at the same time, and then it's obviously going to set timeouts on all of those packets. Yeah, it's going to be a little bit more sophisticated than this. Again, it's obviously different implementations. Right, however, okay, so here then, let's say there is an error with the second one. Now, if there is an error, well, then the receiver is then going to send, well, a nack, right, a negative acknowledgement, obviously kind of back to the server. Sorry, right, back to the sender. Right, so if the sender receives this, and I guess if it receives that, well, before the timeout, well, then of course it's obviously going to send, well, it's just going to resend the data again. Right, so then it's obviously going to send the data again. Let's call this, I don't know, packet 1, right, packet 2. Right, so here then it's obviously resending packet 2. Right, and hopefully then what's going to happen? Well, hopefully the receiver is not going to send a negative acknowledgement in this time. Right, then of course it can wait, let's say for, I don't know, say like 0.6 seconds. Whenever it gets to the next sort of timeout. Then of course, well, then it can send packet 3. Right, now let's say in this case, because there is also another situation. Now, possibly you might have thought, well, actually, what happens if we send a negative acknowledgement? And obviously, let's sort of do that. All right, so okay, let's say here we send a negative acknowledgement, but let's say somewhere on the network there's some error here. So even though we've sent like a sort of negative acknowledgement, we actually haven't received it, right? Sort of, you know, kind of as the sending device. Okay, so if we have this situation, now if we just have the timeout, then actually it's going to get, let's say, to 0.8 seconds, and it's going to think, well, I've not received a negative acknowledgement, right? Therefore, there's sort of no error, right? So that's actually going to be a drawback with, you know, just using a sort of simple negative acknowledgement system. So I think actually in real life they'll actually combine, well, both negative and positive together. All right, but I mean this is obviously just a simple system that only uses negative acknowledgements. Right, although again that is something to be aware of, that we can get this situation. where if the negative acknowledgement is sent but it's not received, well then the sender will actually think that there's been no error, even though there has been. Alright, so let's just try and explain that. So I guess what we can say, let's say what first. Let's say that. Okay, let's say the sender. Alright, the sender, I don't know, yeah, starts a timer. Starts a timer and sends the first packet. Yeah, okay, I know. Let's say sends the first packet right over the network, or by I guess. Okay, yeah, okay. Let's kind of say that it's going to be the computer, right? So the computer starts the timer and sends the first packet right over the network to the printer. Alright, okay. Let's say right. So what if no? Okay, yeah, okay, right. Okay, let's say that. Alright, if the printer, printer receives, right, the packet. Right, and detects, let's say detects no errors. Let's say right, according to e.g. Right, a cyclic redundancy check. Cyclic redundancy check. I guess what calculated. Yeah, okay, right, okay, right. Let's go. Calculated, right, and added to the message, right, by the computer, right, and well checked, right, by the printer. Right, okay, then okay, well, yeah, then nothing will happen. Right, okay, let's say, yeah, else, right, else if an error, right, was detected, right, the printer will send a nack. Well, yeah, okay, all right, let's kind of add that, right, because what we can say, well, if no error is detected, then I guess we'll say what the computer will then send packet to. Okay, yeah, okay, right, so, well, then nothing will happen, right, and when the timeout is reached, or yeah, all right, let's say that, yeah, or when the timer reaches some point, right, let's say when the timeout, right, is reached, right, the computer will assume the message, yeah, was received successfully, right, and will send the next, yeah, I guess we'll send the next packet. Okay, yeah, then else, what if an error was detected, the printer will send right, a negative acknowledgement. Right, negative acknowledgement, I guess what and yeah, okay, all right, what and the computer. All right, okay, let's kind of say right to the computer. Right, to the computer. Okay, what which which will then retransmit that packet. Retransmit that packet over the network. Alright, so I think that should be fine. Alright, now I think I'm also going to mention again what happens if the negative acknowledgement is sent but not received. Let's say that, okay, let's say, right, a potential problem. Right, a potential problem, okay, yeah, problem, right, of only, right, using, well, nacks, right, negative acknowledgement, right, is that, right, if a, well, nack, right, is sent, well, yeah, obviously, well, by the, yeah, right, sent by the receiver, right, but not received by the, well, yeah, okay, well, let's say, right, by the original sender, right, then, well, then the original sender, right, will assume the what packet is, yeah, packets were, or yeah, right, okay, let's say packet, right, was received successfully. Right, okay, let's say what and won't resend it. Yeah, I guess what, yeah, which is I don't know, yeah, which is incorrect or invalid or something. Yeah, I guess maybe incorrect. Right, okay, yeah, then blank page, right, so a computer has system software and application software. Explain how system software is different to application software. Alright, so I guess for this, I mean, basically it's different in high level, low level. Now, system software is low level. That's going to be basically responsible for, well, one, I guess, controlling the hardware. Also, two, I guess we can say things like managing the kind of performance and I guess kind of health of the operating system. So what things like, well, virus checkers, disk defragmenters, yeah, obviously all of the sort of management software, or yeah, the management systems. Alright, so that's going to be, well, the things built into the operating system itself. Yeah, things like in the kernel. So what file management, I guess what kind of like what sort of like resource management, yeah, peripheral management, memory management, yeah, kind of all of those. Right, whereas if we say application software, well, usually that's going to be, well, obviously higher level software. I mean, most of those will be installed by the user themselves. Now, I guess you do also have some built-in ones, let's say like the calculator, or like, yeah, Windows calculator. Or I guess if you got Windows, I mean, Office is probably included. Yeah, I guess most of the time it's included by default. All right, and then of course, any kind of extra application software. So what it could be games, it could be web browsers, it could be, I don't know, graphics editing, like, you know, Photoshop. So let's kind of say that, let's say, right, system software, right, is low-level software, right, responsible for managing, well, yeah, okay. So I guess we're managing, okay. Let's say we're managing or communicating, right, directly with the hardware. Right, let's say what, and I know, let's say, right, maintaining, right, the overall performance, yeah, of the, well, yeah, I guess, yeah, of the operating system. Right, so let's say what, performance, right, or health. Right here, let's say, e.g., I don't know, what's something like, right, disk defragmenters. All right, so hopefully we know what disk defragmenter is, and actually this is only suitable for hard drives. If we have an SSD, then we actually don't need a defragmenter. All right, because, well, we can sort of access any physical location on an SSD, right, in the same time. Whereas if we have a hard drive, well, because of course we actually have the time, well, one, of actually moving the read and write head, two, of course we have to rotate, well, we have to wait for the platter to rotate, right, so it's kind of, well, the correct sector, right, has to be, you know, sort of under the read write head, right, so because we have that physical movement time, well, then we actually have a situation where, let's say, if we have, say, part of the same file that's, you know, split across different parts of the platters, well, then that's actually going to be slow, right, so disk defragmenter, that's kind of what I was saying with the cylinders earlier, right? That's basically going to sort of reorganize the data on the platters, or, yeah, on the hard drive, to actually put it in a way, or, you know, put it sort of in physical locations, right? That's optimized in terms of speed. So again, sort of putting it in the same cylinder, I guess, yeah, maybe putting it in, you know, consecutive sectors, right? Just so it's faster to read, faster to write. So yeah, let's see, right here, well, disk defragmenters, right? Antivirus, yeah, I guess, etc. Alright, so I think that's fine. Alright, and probably here for this low-level software, I mean, let's say, let's sort of give this example. Okay, let's say maybe kernel. Right, I think that's, yeah, I think that's with an E. Yeah, I think it's, yeah, I don't know, I'm sort of not sure. So I think, well, it's obviously kernel with an A, kernel with an E. Yeah, I think operating system, I'm not sure if it's E or an A. Okay, right, let's say a kernel, yeah, I know what kernel, like, code, right, e.g., I know, yeah, file, right, let's say file, well, okay, yeah, okay, let's kind of say the whole thing, right, file management, right, okay, let's say, like, resource management, right, etc. Yeah, okay, so I think that's fine for system software. Let's say, right, let's say in contrast, right, application software, right, is higher level software, right, higher level software, right, that the user, I don't know, sort of interacts with directly, right, interacts with directly, I don't know, let's say for, I guess, productivity, right, or entertainment purposes, right, productivity, I don't know, let's say, right, work, yeah, okay, let's say entertainment purposes, right, purposes, right, etc. All right, and again, let's give examples. Let's say, I don't know, some kind of like office, right, office software, let's say web browsers, yeah, I guess, like games, right, yeah, sort of, I don't know, yeah, like media players, right, etc. Okay, right, so, well, one type of system software is an operating system. One function of an operating system is to manage peripherals. We want to describe the operating system function in managing peripherals. All right, so this is actually quite difficult. Now, I guess what we can say, well, one, the operating system is going to sort of supply some drivers, right? So these drivers, of course, well, that's used basically to provide a way for the operating system to communicate, well, with the actual hardware, or yeah, with the peripheral. All right, now some of those drivers will be built into the operating system. I guess sometimes the operating system also provides a way, let's say, where it can automatically search to find the correct drivers. All right, I guess there's also plug and play, so that means when you plug in the device, well, then the drivers will be automatically installed kind of into the operating system. All right, now I guess we can also say the operating system also stores some kind of like serial numbers related to the device. So that's how, for example, let's say if you plug in, I don't know, say your phone. Well, if you then plug it in again a second time, right, then it can actually remember that you've plugged in your phone again. right? So then maybe it will, I don't know, sort of open some folder that you've, specified it should open, or yeah, it can kind of like remember the settings, yeah, since it's like storing the serial numbers. So yeah, let's kind of say that, all right, and then I guess we can also say it's obviously going to handle the interrupts as well. So yeah, what do we want to say? Okay, let's say right the operating system. Well, okay, let's say the OS. Right, okay, provides I don't know, yeah, a list, or yeah, I don't know, a collection, right, of, let's say, built-in drivers. Right, let's say, as well as maybe like automatic downloads. Well, I guess yeah, okay, right, okay, let's say maybe right automatic. Yeah, okay, right, let's say maybe automatically searching, downloading, maybe installing. Okay, right, let's say, well, via plug-and-play devices. Right, plug-and-play devices, yeah, of relevant drivers. Right, relevant drivers, so the OS can communicate, right, with the, well, yeah, with the peripheral, right, and vice versa. All right, then I think probably we can mention interrupts. That's probably also, well, sort of, yeah, maybe the next important. Right, let's say interrupts, yeah, I guess are also handled, right, by the OS. Right, let's say, for example, I don't know, yeah, for example, like hardware errors. Right, I guess if we're thinking about, let's say, a keyboard, let's say, I don't know, yeah, key presses, right, mouse clicks, yeah, I guess let's go, etc. All right, and then I guess maybe we can mention about the kind of bookkeeping, the yeah, the sort of storing serial numbers. Right, let's say, yeah, also the OS will store, right, store information about the peripheral. Yeah, I guess I don't know, yeah, which can be used, when the peripheral, right, when the peripheral is plugged in again. Or okay, let's say e.g. I don't know, yeah, e.g. like some user settings, right, for that device. All right, and I guess we can say, right, this is achieved. By storing, I don't know, again, some kind of serial number or a unique ID. Yeah, or let's say a serial number. Or well, okay, right, let's say so the serial number. Right, of the peripheral. Yeah, I guess in the OS. Okay, yeah, that's fine, right? So then C, we want to complete the table by giving 2 examples of software security solutions and explain how each protects against computer threats. Alright, so I think for this there's really just 2, right? So we can say firewall, and I guess we can also say antivirus. Alright, so let's just go ahead and write those quickly. Let's go, for example, firewall first. Okay, where's the text? Okay, there we go. Right, okay, let's say firewall. Alright, and then let's just go across here. Alright, okay, right, okay, so here then, well, this is 6 marks. They do want probably maybe 2 marks for the actual, well, the sort of name. Then I guess about 4 marks, right? So 2 marks each for each explanation. Alright, so I guess a firewall, we can say basically that's going to control, well, the packets that come in and out of a, kind of in and out of a computer, right? And I guess also in and out of a network. Because if we think, well, there's going to be a software firewall on your computer, right? But most likely the router itself is also going to have a firewall, or yeah, the sort of network. Alright, so yeah, let's say that. Right here, let's say, right, it's used, alright, to control, right, let's say, well, accept, right, or deny, right, the, well, I guess, yeah, the packets, let's say, well, yeah, I guess coming in, right, coming into, right, or leaving, right, a network. Yeah, I guess what, I don't know, to ensure, I don't know what, to ensure like malicious, yeah, I don't know what, to ensure like malicious activity, yeah, is avoided. Alright, and then I guess we can give examples of like how this is done. So we can say, well, again, it's based on the protocol, based on the port, yeah, based on the IP address, right? Of course, we can have a blacklist. Yeah, okay, let's say that, right, let's say specific rules. Can be set up, alright, to e.g. I don't know, maybe what disallow certain programs, right, from internet access. Alright, so if, for example, you have Windows, well, just type in, sort of firewall, right, in the Windows settings. Then again, you should be able to see this. You can obviously search, well, yeah, search the different programs that are allowed. Again, you can, sort of block port numbers, right, block protocols. yeah, I guess block IP addresses, right, etc. Right, okay, yeah, so disallow certain programs from internet access. Let's say, right, block, well, all right, okay, let's say create a blacklist. Yeah, so a blacklist, right, whitelist, right, of IPs, right? So if we say a blacklist, well, of course, that's IP addresses that are not allowed. So yeah, IP addresses we're not allowed to download from, right? IP addresses we're not allowed to send to, right? If we have a whitelist, well, that's a list that we are allowed to send to. Right, so if, for example, you're I don't know, you're sort of like let's say some kind of regular user, well, then you would just want a blacklist, right? Because probably you can assume, let's say, like 99% of IP addresses are sort of safe, right? That you can communicate with them. Right, now, let's say I don't know, there's some website which you want to block. Maybe you're in a school setting, and yeah, you also obviously want to block certain websites. Well, then you could, for example, create a blacklist of website IPs that you want to block. Right, now, if, for example, you're in some high security setting where maybe you have some like critical server, and you say, well, this server should only be able to communicate with this whitelist of one, or let's say like 5 different IPs, right? So that's generally when you'd have the difference. Right, so if you have a blacklist, I mean, usually that's when, let's say, most IP addresses you will allow, and then only a few you want to blacklist. Whereas a whitelist, that's the opposite, where most you want to disallow, right, and only a few you want to allow. Right, so that's obviously going to be safer using a whitelist. Anyway, right, create a blacklist, whitelist for IPs. Let's say, I don't know, yeah, disallowed, right, ports, right, protocols, right, etc. All right, then I guess we can say, well, the firewall can operate both on the computer and I guess on the router. Right, okay, so okay, all right, okay, yeah, let's right, firewalls. Okay, yeah, firewalls right are commonly I guess placed. Right, placed on I guess both I don't know what sort of both end devices. Right, end devices, right, like computers. Right, and also what the network router itself. Yeah, I guess or the network gateway. Right, the network gateway, itself. All right, so when we say the gateway, well, again, that's basically going to be the entrance into the network. Now, if you're talking about a home environment, well, that's just going to be the router, right? If you've got, I don't know, some complex like business environment with maybe hundreds of different devices, well, maybe you'd have some kind of dedicated gateway, and then that gateway would then forward onto different routers. But yeah, I mean it's like it's sort of usually the same thing, right? In most cases, the gateway and router is just the entrance to the network. All right, so I think hopefully that's enough for 2 marks, right? Then the next one, well, let's go antivirus. Well, I guess antivirus or anti-malware. Let's kind of say both of that, I guess. Because it's okay. So actually, it seems for Cambridge they prefer using the term malware, because if you think, well, malware, that encompasses all the different types of malicious software. So viruses, trojans, I guess sort of spyware or adware. I guess ransomware. Worms. Right. Whereas if we say virus, well, again, obviously that's talking about just a specific thing. Right, so if you don't know the difference between all of those, what a worm, well, that's going to be something that can spread throughout the network. A virus, well, that's going to spread just on one device. A Trojan, well, that's basically some malicious code that hides inside a file. So just like the Trojan horse, right? As I know the Greeks or like Troy Spartans, whenever that was from. So obviously hides inside a file. So let's say you have I don't know, like Microsoft Word, but you actually have some like malicious version of Word, which someone has embedded with some sort of malicious software inside, right? That's going to be a Trojan. Then I guess spyware, that's going to, let's say, record your keys. Maybe it'll try to record your passwords. If you've got some like crypto wallet, right? Maybe it can try and sort of steal the private keys, right? Things like that. So obviously, just trying to steal data. I guess adware, well, that's obviously just going to sort of show loads of ads, obviously trying to make money by showing ads. And then I guess ransomware, what that can obviously encrypt all the files on your computer or on your device. Then it will ask for a payment, right, in order to get the decryption key, in order for you to decrypt your files and obviously get access to them again. Alright, okay, so let's kind of do it then for antivirus. So what we can say, basically, this will maintain a database of kind of known malicious software. I guess it can do that based on, for example, hashes. So if it knows, this file with this hash is malicious, well, then of course that'll be in the database. That's why basically the antivirus should be updating quite regularly, probably like daily or weekly, just with all the latest known viruses. Or I guess it can also then do what's called heuristic analysis. That's basically checking the behavior of the program. So if, for example, you have some program that's like, let's say, like opening loads of files, like sort of like, hundreds of files per second, right? It's then modifying those files and then writing them again. Well, that's obviously going to be typical behavior of, let's say, ransomware. Right, now it's not guaranteed. I mean, that could just be some like legitimate encryptor. I guess it could just be a zip file, or some like zip, zip processor or archiver. Right, now I guess the difference is what an archiver, that's going to be reading lots of files, but then it's actually only going to be creating one zip. It's obviously not going to be like overwriting the original files. Right, so if that's kind of what it means when we say heuristics, well, checking the behavior of the program. Right, now let's say we have some program that's sending like gigabytes and gigabytes of data. Well, that could be an example of say some kind of spyware, right? They're sending all of the files on your system, right, to to the hackers kind of server. Right, so let's do that. Okay, so let's write this program. Right here, this program. Can or let's say can or will, right? Let's say can. Okay, right, can. Let's say right automatically. Scan new files, right, e.g. downloads. Be scheduled. Okay, right, let's say we're scheduled by the user, or according to a schedule. All right, okay, by the user to scan the whole, right, or parts of the system. Parts of the of this. Let's say parts of the file system. To check for malicious files. Let's say malicious files, right, or malware. Right, and then let's see how this is determined. Let's say this is determined. So check for malicious files. Okay, right, let's say according to. Let's say according to either, right, a database, right, of known malicious files. Malicious, files. Hashes, or I guess kind of like assembly, sort of like machine code, machine code, kind of like, extracts, right, because you might not necessarily have the whole file which is identical, because generally if you're a hacker, I mean, it's probably not a good idea, let's say, to create one, one malicious file and then, send it to every single person. Right, what might be better is if you actually sort of add some random data in there, or change the file slightly, because then if you're doing a simple hash check, well then obviously your say malicious file is going to be different from another person's malicious file. It's obviously not going to match the same hash, right? So I think antiviruses usually what they'll do, they'll actually scan for, let's say, specific kind of sections of machine code, which are known to be malicious. So let's say that, right, according to either a database of known malicious files, hashes, or sections, right, of known malicious machine code. So I think that's fine. Okay, let's say alternatively, like behavioral, behavioral heuristics can also be used. As the program is running. Be used, as the process, or the program, right, is active. Obviously active means running. Okay, right, running, to determine, if the behavior, behavior is suspicious. Let's say, e.g., opening, let's say opening, modifying, and rewriting, let's say, huge numbers of files. If the behavior is suspicious, right, and indicative. I think maybe that's an A. I'm not sure how to spell that, right. Indicative, of malware. Then D. So then we just want to define the terms firmware and operating system. Right. So if we say firmware, basically that's going to be the low-level code that's used to directly manage the hardware. So let's say that. Let's say the low-level code. That is used to directly manage, right, the hardware. Alright, so I guess if we sort of want to give an example, alright, and actually I guess we could be more specific. So let's say this. Alright, let's say the low-level code, I guess, that operates on, let's say that, right, that operates on and is used to directly manage the hardware. That operates on and is used to directly manage the hardware. Okay, let's say for example, let's say a printer, will yeah, will have firmware. Right, okay, let's say which kind of decodes. Right, let's say which decodes what the input file format. Yeah, the kind of input, let's say, print. Okay, it was kind of like a printer language format. Right, okay, okay, right, okay, all right, and then I guess we say and rasterizes it. Right, so when we say rasterizes, that's basically converting some format, let's say like a PDF or yeah, some kind of like vector format into a format that's basically pixels. Okay, so yeah, let's go rasterizes. Right, this into I don't know what, just like pixel data. Right, pixel data. Right, that I don't know. Yeah, that the printer can use. Right, the printer can use. I don't know what sort of like when controlling or yeah, when printing. Yeah, all right. Let's say when controlling the ink or something, or I don't know. Yeah, okay. When controlling the motors. Alright, so I guess that's also going to be the other part. Alright, so as well as the actual kind of, let's say, like general software component, which that's like decoding, or yeah, the actual like logic of the logic of the hardware. We also have the actual kind of even lower level signals in many ways, which again that's like send a signal to the motor, right, to again obviously change the speed, change the direction. So yeah, okay. For example, print will have firmware that which decodes the input print. Decodes the input printer language format, and rasterize this into pixel data that the printer can use when controlling the motors. Yeah, okay, right. This is kind of terrible grammar. Okay, let's say let's say controlling. Controlling the motors. And other hardware. Yeah, I guess hardware or like mechanics. Is also the responsibility. Of the firmware. Right, right. So here then, the operating system, I guess we can say what is used to provide an interface between the user and the hardware. And again, we can also mention system software, application software. Right, let's say, let's say, yeah, it is used to provide an interface. Let's say interface. Let's say input and output between the user, and hardware. Yeah, I think that's fine. All right, and then I guess we can say, for example, some tasks that the OS is responsible for. Let's go in what includes, and then again, let's think of all the management tasks. So let's go file management. I guess resource management. Management. I guess we can say peripheral management. Peripheral management. Let's say memory management. So memory management. Yeah, is there a few more? All right, so I think sometimes they also say security management. I think that's really the main ones. Yeah, my mind has sort of gone blank. All right, but if you want to sort of check the book, yeah, of course, just sort of make sure I haven't missed any of those. Okay, then finally 9, and let's just see how much more we have. Okay, yeah, just one page. Right, so it says a programmer is writing a program using an integrated development environment, R or IDE. The program will take data from barcodes as input. A barcode includes a check digit. We want to explain how the check digit is used to check for errors in data entry. Okay, so I think for this question, what we can say, basically, the check digit is calculated to a pre-known algorithm. For example, that can be a sum, it can be modulus. Of course, that's going to operate on the input data, right? That will then produce one check digit, right? One digit as output, and that's obviously done by, I guess, the sort of barcode when it's created. By the system that creates the barcode. Then obviously when the barcode is scanned, then the scanner, that's obviously going to have some software inside it, or maybe inside the computer. That's obviously then going to scan the barcodes. It's going to decode them. It's then obviously going to perform the same algorithm. Again, it's obviously going to check the check digit, right? If they match, then it can assume there's no errors. Obviously, if they don't match, then it will assume there is an error. So yeah, let's try and write that. Let's say when the barcode is created, let's say an algorithm, let's say operating on the input data. Let's say e.g. I don't know, summing. Summing, and modding. Like values. Let's say is performed. And I guess a single number. A single number. Right, now this doesn't necessarily just have to be one digit. It could be some, I don't know, some longer check digit, right? But if we think, let's say like ISBN, right, so the books, I guess also barcodes, right? I think in those cases they are both going to be one digit, yeah, although it sort of doesn't necessarily have to be. Okay, yes, are performed, right, and a single number, well, okay, yeah, let's say what the check digit, right, is calculated. Right here, yeah, okay, that's fine. Let's see what when the scanner, okay, right, when the scanner well, scans the barcode. Well, I guess yeah. Well, sort of when the okay, right. Let's say when the program. Okay, right. Okay, yeah. Okay, let's say that, right. So when the scanner scans the barcode, right, and the right data is well fed into the program. Right, fed into the program. What the program performs the same. Right, performs the same check digit calculation. Right, I guess what and yeah recalculates the check digit. Right, recalculates the check digit. Okay, well check digit. Okay, right. Okay, so if the check digit, right, if the check digit is the same as the check digit, I guess what on the original barcode. Yeah. Okay. Let's say right. So if the calculated check digit. Right, if the calculated check digit is the same as the original check digit, well, yeah, okay, right, so, well, the check digit on the barcode, right, then we can assume, right, the data, right, has been read correctly. Right, and then, okay, let's say if they're different, right, if the check digits, yeah, if the check digit, yeah, digits are different, right, we can assume, right, there has been an error. Yeah, I guess an error in reading the data. Yeah, okay. Alright, so it's sort of, well, not guaranteed that there's an error because I guess it could be an error when we've actually read the check digit. But yeah, I guess most likely it's an error when, you know, we've been sort of reading the data. Okay, B, so the program is using a high-level language to write the program. Describe what is meant by a high-level language. Alright, so basically we can say it's using kind of English-like words or, yeah, kind of common language words. Okay, let's say that right, the programming language right, consists of, I don't know, okay, or let's say maybe English-like, well, I guess kind of, okay, okay, let's say human, yeah, human language, or like e.g. English. Yeah, I guess, well, kind of like words. Yeah, I guess, well, sort of, I don't know, okay, okay, let's say keywords, right, function names. Well, yeah, okay, right, let's say maybe module names. It seems Cambridge, they prefer to say module, because, well, module, they say is, you know, function and procedure. Whereas obviously function is, well, yeah, just a module that returns a value. Okay, yeah, module names. Yeah, I guess etc. Yeah, I think that's fine. Right, okay, and then let's talk about, we can say, well, one statement often is equivalent to many assembly instructions. Let's say, right, one, I don't know, yeah, one statement. Right, okay, let's say e.g. Okay, let's say like a dot sort method. Right, in many language, yeah, many languages. Right, is often equivalent, right, to a large, right, a large number, yeah, of sort of machine code. Okay, well, let's say I don't know, let's say assembly, right, / machine code instructions. Yeah, I mean that okay. So that's kind of generally true. All right, now let's say we have I don't know, some simple assignment, like, you know, sort of X, and then assign that 5. I mean, that's only going to be like one, you know, assembly instruction or one machine code instruction. But again, if for example we have some sort, I mean, realistically, that's going to be like thousands of instructions most likely. Yes, okay. So especially when you think most programming languages, they actually don't just use one sorting method. They actually sort of check, well, what's the data type. They check the size of the array, and then they sort of, you know, choose a specific sorting algorithm. Yeah, they're sort of, you know, going to be the most efficient, right, for this particular data type, yeah, for this particular, well, kind of, you know, size of array, etc. Alright, so I think that's probably okay. I mean, possibly you could give examples. I mean, they're not really going to give marks for that, but I guess let's just add it anyway. Let's go add it. Yeah, examples include, and then we can say what Java, well, VB, right, and Python, right. So the 3 examples that they also support, yeah, on the syllabus. Okay, then the final one. So the programmer uses a compiler during the development of the program. Describe the benefits of using a compiler when developing the program. Alright, so this is a bit strange because often they say, well, sort of like after developing or, when sort of distributing the program. Alright, now I think here they probably are talking about distributing as well. So if we're saying a compiler, well, basically it's going to produce an executable. So that's going to be easier to distribute because, well, the kind of end user, well, they're not going to need some interpreter installed on their system. Because if we think, well, most normal users, let's say they're not going to have, let's say, like the Python, the Python interpreter installed on their system, or they're not going to have, I don't know, some, more, some like even less, common language installed on their system, right? Whereas if we just send them like an exe on Windows, well, then of course, I mean, well, they're sort of going to be able to run that. I guess as long as it's the correct the correct architecture, the correct CPU architecture. Right, so that's going to be one benefit. Okay, the second benefit, well, it's also going to be faster. So an executable is, well, sort of compiled executable, right, should always be faster than a kind of interpreted language. I guess we'll sort of assuming the compiler is good and can produce optimized code. All right, and then I think also we can also mention it's harder to reverse engineer because if, for example, we're using an interpreter, well, then we have to send them the source code. Now, if you're some company that obviously has, some I don't know. You've obviously been spending, like many years developing this program. You've got, say like lots of people working on this program. Well, probably you don't want to distribute the source code because, well, then of course people can just copy it. They can, sort of use it as their own. All right. So if you just send the executable, well, then of course they can see the machine code. I guess they could use a sort of disassembler. That can then sort of try to convert it back into some kind of assembly. But even so, it's still generally going to be a lot more difficult. All right, so I think probably that's the three. So we can say, again, that's kind of good for privacy, right? Good for their intellectual property. So let's say that, right, distributing the program, is easier, right? Since just a single executable file, right, needs to be sent to the end users. Let's say right they also don't have to have the interpreter installed on their system. Have the interpreter installed installed on their system. Let's sort of say why that's a good thing. Well, why it's good they don't need the interpreter. Let's say which I guess which is not likely. Which is not likely, right, that what sort of like normal users will have this installed. Let's say secondly, I think that's probably everything really. Let's say secondly, I guess what compiled programs, should be faster, right, than interpreted programs. I guess what interpreted programs, assuming the compiler sort of produces sort of fairly optimized code. And then I guess finally, let's say finally, since just the executable is sent, then I guess what the company, or well the company, right, slash developer, I guess can maintain, right, their intellectual property, intellectual property, I guess what's sort of more likely. So since just the executable was sent, then, well, let's sort of reword that. Let's say then, then it's harder, right, for sort of end users, to reverse engineer, hence I guess compromising compromising the intellectual property. I don't know what. Let's say by by copying, and sort of distributing it as their own, distributing it as their own. Let's kind of change that. Let's say copying while modifying. Modifying, and redistributing as their own, right? Because I guess even if it's an executable, well, of course, people can still send that to other people, but they can't really modify. They can't add their own features and then obviously claim it's their own. Okay, yeah, so I guess, right, okay, that should be compromising, not comprising. Okay, yeah, all right, let's just change that. All right, so, okay, compromising the intellectual property. Yeah, okay, all right, let's read this again. Right, finally, since just the executable is sent, right, then it's harder for end users to reverse engineer. Hence, compromising the intellectual property, yeah, I guess, I don't know, yeah, of the software. Yeah, I think that's fine. All right, so I guess we could say in contrast, right? I don't know, in contrast, right, to interpreted programs, right? Okay, where where the source code, right, also has to be sent. All right, so I think that's everything. Right now, guys, I think that video is super long. Hopefully that's useful. All right, and again, I'll see you in the next video. All right, and hopefully I should upload the P2, hopefully within maybe 2 or 3 days. Yeah, just whenever I have time.